Hey there, it's really nice to have you back with me tonight. Maybe you found this video by accident scrolling through your phone somewhere in the dark, or maybe you have been waiting for it all day, saving it for exactly this moment, right before your eyes finally get too heavy to stay open. Either way, I am glad you're here settled in ready to slow all the way down for a little while, because tonight I want to take you somewhere strange. A stretch of time so quiet, so still that scientists eventually gave up trying to make it sound exciting and just gave it a nickname instead. They called it the boring billion, a whole billion years where almost nothing seemed to happen. No oceans ripping open, no mountains rising overnight, no headline moments if rocks could ever write headlines. Just silence stretched across a length of time longer than your mind can really hold on to. But stay with me for a moment. Because what if the quietest chapter our planet ever lived through was actually hiding the biggest secret of all? Before we slip into that story, though, I want to ask you for a small favour. If you are the kind of person who loves these slow, quiet walks through deep time, it would mean a lot if you tapped that subscribe button, left a like or dropped a comment down below, and I would really love to know a little about you tonight. Where are you watching from? Are you already curled up under a blanket riding somewhere in the passenger seat, or lying in bed with your eyes half shut? Tell me down in the comments or just leave me a kind word. I look through every single one and it always makes my night a little warmer. Now go ahead and turn the lights down low. Maybe switch on a fan or some soft background noise, just enough to make the room feel a little more like a dream. Get comfortable wherever you are tonight, because this story begins somewhere you probably never expected. Picture Earth 1.8 billion years ago. Not the Earth you know, no green coastlines, no white clouds drifting over blue water the way you might picture from an airplane window somewhere over the ocean. Just a planet turning quietly through the dark, carrying seas that shimmer with strange colours we will get to a little later tonight. If you took the entire 4.5 billion year story of our planet and folded it down into a single day, this next part, the part we're about to spend our whole evening inside, would take up almost 5 hours of that day. 5 hours out of 24 where almost nothing changed at all. Try holding that thought for a second. 5 hours of a single day and the scenery barely moves. Here is another way to feel the size of it. All of recorded human history, every pyramid, every empire, every single love letter ever written, fits inside roughly 10,000 years. You could take that entire stretch of human history and fit it inside this 1 billion year silence about 100,000 times over. 100,000 entire human civilizations stacked one after another, and it would still only fill this single quiet chapter of our planet's life. Now imagine standing on a shoreline during that stretch. The sky above you is not blue the way you would expect. There is far less oxygen drifting through that air, so the light behaves differently, softer somehow, almost heavy, the way a room looks right before a storm rolls in. The water in front of you laps gently against dark ancient stone, but there is no seagull sound, no distant boat engine, no human voice anywhere on the entire planet. Just water rock, and a silence so complete it almost has a weight of its own. And somewhere beneath the surface of that water, a colour is quietly forming one most of us have never even considered an ocean could hold. We will step into that part of the story a little later. For tonight, just notice the stillness. That is where we are. Geologists have another name for this era too. Some call it Earth's Middle Ages, a term given by researchers who notice something odd about it. During this stretch, the rock record barely moves. No dramatic swings, no sudden spikes, just a long flat line on every graph they draw like a heartbeat monitor that refuses to change no matter what happens around it. There is a paleontologist named Martin Brazier who is usually credited with putting a name to this strange quiet, the boring billion. And once that name stuck, it stuck hard. For years, most researchers simply moved past this era, too still to study closely, too uneventful to build a whole career around. Almost embarrassing in a strange way for a planet that has once been so wild, and would soon become so wild again. If a streaming service had existed back then, someone in an editing room would have quietly cancelled this billion years for having absolutely no plot. Because here is the thing you need to understand first. This billion years of silence did not come out of nowhere. Right before it began, Earth had just survived something almost violent. Its atmosphere had gone through a transformation so extreme, it would have poisoned nearly every living thing that existed at the time. And right after this quiet billion years finally ended, the planet would freeze over so completely that some scientists believe ice reached almost all the way down to the equator. So picture it this way, a wild beginning. Then this long, strange pause, then chaos again waiting patiently on the other side like a storm that simply paused to catch its breath. You probably know someone like this in your own life. That one friend who never seems to carry any drama with them. No sudden career changes, no dramatic breakups, no wild stories to share when everyone catches up over coffee. Just calm, steady, always, exactly the same person you remember from years ago. And sometimes, without even meaning to, you start assuming their life must be a little dull, maybe even a little empty. Or maybe it feels more like a certain kind of year in your own life. One of those years where nothing seems worth writing down. No big moves, no new job, no dramatic ending or beginning. Just Tuesday, then Wednesday, then Tuesday again on repeat for months. We tend to file those years away as wasted time, as if quiet automatically means nothing was happening beneath the surface. Maybe you're inside a year like that right now. If you are, I hope tonight's story gives you a small piece of comfort, because we live in a world that keeps score out loud. Promotions get announced, milestones get posted with photos and captions and little rows of hearts underneath them, and when your own life feels more like a still photograph than a highlight reel, it is easy to start believing that stillness is the same thing as standing still going nowhere at all. Earth, it turns out, might be the oldest possible proof that this simply is not true. Because this particular planet held on to its own quiet, ordinary pattern for one full, uninterrupted billion years. During this time, the air did not gain much more oxygen than it already had. The ocean stayed roughly the same strange low-oxygen version of themselves, stretch after stretch, century after century. The land slowly drifted together into a single, slow, moving supercontinent, and then it mostly just sat there, barely shifting at all for hundreds of millions of years. Life on Earth was almost entirely made up of small, simple organisms, quietly repeating the same patterns their ancestors had followed for millions of years before them. No dinosaurs yet. Nothing like them at all, not for another billion years or more. No plants standing tall on dry land. No creatures crawling out of the water to look up at the sky for the very first time. Just an ocean, and whatever lived quietly inside it day after day for what must have felt to anything capable of feeling like forever. If you could rise up above the clouds and look down at this planet from orbit, you would barely recognize it as home. One single enormous landmass sits alone in the middle of a vast dark ocean. Its surface a dull rust-red and dusty brown bare rock, with no green anywhere because nothing green has learned how to live on land yet. No forests, no grass, no sound of birds because birds will not exist for well over 1 billion years still to come. Just dust drifting quietly across bare stone and silence answering back. And if you happen to look up instead of down on a clear night along that quiet shoreline, you would notice the moon hanging closer and looking noticeably bigger than the one you're used to seeing tonight. Back then, days themselves were shorter too, somewhere around 18 or 19 hours long, spinning by a little faster than the days we count on now. Slowly, over unimaginable stretches of time, the moon has been drifting a little farther away, and our days have been gently stretching out to catch up with it. Even time itself was still finding its rhythm. For a long time, that was the entire story scientists told about this billion years. Nothing happened here. Move along. Some researchers even joked that studying this era felt a little like watching paint dry, except the paint took a billion years, and nobody could quite agree on what colour it even was. But this is where it gets interesting, and it is the part I really want you to sit with for a moment. In just the last few years, researchers went back and looked at this so-called boring stretch of time with completely fresh eyes. New tools, better technology, sharper questions tested against ancient rock samples pulled from places like the shoreline near Lake Superior, sitting quietly in laboratory drawers for decades before anyone thought to look at them closely again. And what they found has quietly begun to rewrite everything we thought we understood. It turns out this billion years may not have been empty at all. It may have been the slow, patient setup for everything that came after it. Every animal, every plant, every complicated form of life you can picture right now, including the one currently listening to my voice tucked into a blanket somewhere halfway to sleep. All of it may trace back to something that was quietly taking shape piece by piece during this so-called boring stretch of time. Think about that for a second. Somewhere in that silence, without any dramatic turning point, without a single moment anyone could point to and say, "This is where everything changed." The foundation for you was being laid down, not loudly, not suddenly. Just patiently, the way roots grow underground, long before anyone above the soil notices a single leaf. We're going to spend the rest of tonight's journey walking through exactly how that happened. I promise you that. But not yet. Tonight, in this first part of our story, I just want you to sit inside the quiet with me for a while longer. I want you to really feel what it might have been like to stand on that shoreline 1.5 billion years ago, bare feet against cold, dark stone, and look out at a world that felt like it was holding its breath. No breeze moving across the water, no sound at all except the smallest, softest lapping of waves against rock, over and over, endlessly patient the way a clock keeps time even when nobody's watching it. Somewhere far off, the huge dim shape of that one lonely landmass sits under a sky with far more stars in it than you've ever seen, because there is no city glow anywhere on the entire planet to dim them. Just you if you had somehow been standing there. Just water and stone and that enormous oversized moon, quietly pulling the tide in and out and in again. Because before we can understand why that silence mattered so much, we need to understand exactly where it came from. We need to go back a little further to the version of Earth that came right before it finally went still. A planet that had just survived something bordering on catastrophe. Something loud and dangerous and almost impossible to imagine now. From inside this softer, quieter chapter, we're about to spend the rest of tonight exploring together. So let's actually go there. Let's rewind the clock a little further back than we have gone so far tonight, past the shoreline, past the quiet, back to the version of this planet that had to exist first, before any of that stillness was even possible. Because nothing gets to be calm without earning it first, and Earth, believe me, earned this one the hard way. Picture a much younger version of our planet somewhere near 2.5 billion years ago. The sky above you is not blue. It is not even grey. It is a strange hazy amber, almost the colour of weak tea held up to a lamp thick with a gas most of us barely think about today. Methane. Lots of it. If that description sounds oddly familiar, there is a reason for that. Astronomers studying Titan, one of Saturn's larger moons, describe its sky in almost exactly the same hazy orange terms today. In a strange way, an early photograph of our own planet, if such a thing existed, might have looked less like home and more like a snapshot from somewhere billions of miles away. And here is a small strange comfort for you. Back then, the sun itself was actually dimmer, somewhere around a quarter less bright than the one warming your house right now. By all logic, this planet should have been frozen solid. Instead, that thick blanket of methane in the sky was doing exactly what a blanket does, trapping just enough heat to keep the oceans liquid, keep everything ticking along, keep the whole fragile experiment of life quietly running. And underneath that amber sky, life already existed. Simple, single-celled, mostly hidden beneath the water, breathing in a way that would kill you or me in minutes if we tried it. No oxygen involved at all. These early organisms pulled their energy from sulfur, from iron, from chemistry. We rarely think about, and they had been doing exactly that, more or less unchanged, for well over 1 billion years already. Can you imagine that 1 billion years of one kind of breathing, one kind of life, one steady rhythm before anything changes at all? Then quietly, almost apologetically, something new showed up. A tiny organism, smaller than anything your eye could ever catch, learned a trick no living thing had ever pulled off before. It figured out how to take ordinary water and sunlight and turn them into food while breathing out a strange gas as its leftover waste. That gas was oxygen. And the organism was cyanobacteria, sometimes still called blue-green algae, even though it is not really algae at all. You can actually still see their living descendants today if you know where to look. Along the warm, shallow coastline of Shark Bay in Western Australia, there are strange rounded mounds of rock rising out of the water layer, stacked upon layer, built one thin sheet at a time by colonies of cyanobacteria, going about their business exactly the way their ancestors did 2.5 billion years ago. Scientists call these structures stromatolites, and standing beside one today is about as near as any of us will ever get to shaking hands with the organism that changed the entire planet. Have you ever stood somewhere that felt truly older than everything around it, a place where you could almost feel how much time had passed just by looking at it? That is exactly what a visit to Shark Bay apparently feels like, according to people who have made the trip. Here is something else worth sitting with for a moment. Cyanobacteria did not transform the planet overnight, even after they learned this new trick. Researchers estimate they had already been quietly producing oxygen for something near 300 million years before that oxygen ever built up enough to matter globally. For most of that stretch, the oxygen stayed trapped in small local pockets, sometimes called oxygen ORCs, tiny bubbles of a completely different atmosphere hiding inside an otherwise unchanged world. It is a strange thought that the future of this entire planet was already forming in these small scattered corners, long before anything could have possibly noticed. At first, this new gas oxygen barely mattered. The ocean simply swallowed it. Dissolved iron drifting through that ancient water in huge quantities reacted with the fresh oxygen almost instantly, the way an old nail rusts if you leave it out in the rain. Layer after layer of this rusted iron settled quietly onto the seafloor, red and grey bands stacking up over millions of years, forming what geologists now call banded iron formations. Here is a small detail I happen to love. Those very same rust-coloured layers formed in oceans that existed before a single blade of grass ever grew on land are the reason you can find steel in your car, your kitchen, maybe the frame of the bed you are lying in right now. Something about that feels almost impossible to me, that so much of the modern world is quietly built from the rusted leftovers of a 2.5 billion-year-old chemistry experiment. But oceans, as patient as they are, cannot absorb forever. Eventually all that dissolved iron ran out, and oxygen with nowhere left to go started rising up out of the water and into the open air. This is the moment scientists now call the Great Oxidation Event. It happened roughly 2.4 billion years ago, and it unfolded slowly stretched out across hundreds of thousands of years, not overnight, though the outcome for most of the life on this planet may as well have been overnight. Because here is the part that always stops me for a second whenever I think about it. Oxygen, the very thing every single one of us needs to survive right now tonight. Breathing quietly in your bed was for nearly every living thing on Earth at that time a poison. A real planet-spanning catastrophic poison. To an organism that had spent well over 1 billion years perfecting a life without oxygen, this new gas did not feel like a gift. It felt like the air itself had turned against them. Some scientists now consider this the very first mass extinction in the entire history of life on Earth, long before anything with a face, a shell, or a backbone ever existed to record it. Not every anaerobic organism disappeared, though. Some retreated. Deep mud at the bottom of lakes, scalding hot springs, cracks in the seafloor where scorching water still pours out today. Even strangely enough, the quiet darkness inside your own body, since your gut is still home to countless organisms that have never once needed oxygen to survive. In a small hidden way, that ancient poisoned world never fully ended. It just learned to hide. Have you ever had something enter your life that was supposed to help, and at first it only seemed to make everything harder? A move to a new city, a relationship ending that you swore at the time would ruin you completely. I think about the Great Oxidation Event a little like that sometimes. The very thing that would eventually make every complex form of life possible, every animal, every one of us, arrived first as an absolute catastrophe for almost everything alive to witness it. And the story does not slow down there. Oxygen did something else once it reached the open sky, something almost nobody expects the first time they hear it. It began quietly reacting with all that atmospheric methane, the very same gas that had been keeping this planet warm for longer than anyone alive could ever picture. Methane broke down into carbon dioxide and water vapor, both far weaker at trapping heat. And that thick amber blanket keeping Earth warm despite its fainter younger sun began to unravel. The planet started cooling. Slowly at first. Then it didn't stop. Ice crept outward from the poles, spreading further than almost anyone studying these ancient rocks originally expected. Some researchers who have examined the layered stone left behind from this era believe the ice may have reached surprisingly near the equator itself, wrapping much of the planet in white. This is what we now call the Huronian glaciation, named for the Huron supergroup, a stretch of ancient rock formations in what is now Ontario in Canada, where geologists first pieced this story together from stripes of stone laid down by advancing and retreating ice. Here is something that quietly reshaped how I picture this whole era. For a long time, people imagined the Huronian glaciation as one single unbroken freeze, one long white winter, lasting hundreds of millions of years without pause. But the rock layers themselves tell a messier, more honest story. They show ice, then thaw, then ice again, at least 3 separate times, maybe more stacked one on top of another, like chapters nobody fully finished reading. It was not one long silence. It was closer to a planet stumbling forward, freezing, recovering and freezing all over again, still trying to find its footing. Depending on which layer of rock you trust most, this whole frozen stretch lasted somewhere near 200 or 300 million years. Sit with that for just a second. Not 200 or 300 years, 200 or 300 million. An ice age so long that if you tried to walk through it 1 year at a time, you would still be walking long after everyone you've ever loved, and everyone they ever loved before them had come and gone many, many times over. For a little perspective, the ice age you and I would recognize, the one that shaped the woolly mammoths, The great glaciers carving out lakes across the northern half of this continent only began around 2.5 million years ago, and it is technically still going on quietly in the ice sheets covering Greenland and Antarctica right now. Compared to the Huronian glaciation, that entire familiar ice age is barely a passing afternoon. Everything moved differently back then too, in ways that still catch me off guard. The Earth spun much faster in those days, so much faster that a single day sunrise to sunrise lasted somewhere around 11 hours, not 24. If you remember me mentioning a little earlier tonight that days during the boring billion stretched to around 18 or 19 hours, you are already starting to feel it. Time itself has been slowly stretching out one impossibly small heartbeat at a time for billions of years, and it was only just getting started back here. So how does something frozen, that deeply for that long, ever thaw out again? Here is where the story turns almost gentle for a moment. Underneath all that ice, the planet never stopped breathing. Volcanoes kept quietly releasing carbon dioxide the way they always had, but with the entire surface locked under ice, the normal process that usually pulls carbon dioxide back out of the air rock, slowly weathering in the rain, simply could not happen anymore. So the gas kept building. Century after century, buried under a white frozen silence, the planet was slowly, patiently gathering exactly what it needed to warm itself back up again. I find something quietly moving about that, if I am honest with you. The very disaster that froze this world also carried hidden somewhere inside it the beginning of its own undoing. Maybe you know a season like that too, one that felt unbearable while you were living through it, but that was already without you fully realizing it, building the thing that would eventually pull you back out again. Eventually, after all those hundreds of millions of years, the carbon dioxide won. The ice retreated. The oceans opened back up beneath a sky that finally had real breathable oxygen drifting through it, though still nowhere near the amount we enjoy without a second thought tonight. Here is a mistake almost everyone makes the first time they hear this story, myself included the very first time someone explained it to me. It is easy to assume that once oxygen filled the sky, complicated life must have followed fairly quickly, after animals, plants, something with eyes finally arriving to enjoy all that hard-won breathable air. That is not remotely what happened. The first true animals would not appear for well over 1 billion years after this ice finally melted. An entire additional 1 billion years on top of everything you have already heard about tonight, standing quietly between one planet, learning to breathe and anything on it, actually using that breath to move to hunt to grow a single working eye. Oxygen alone, it turns out, was never going to be enough. Something else, something slower and far less dramatic still had to happen first, and Earth, after surviving a poisoning and an ice age that stretched across a length of time almost too large to hold in your mind, finally slowly began to settle. The wild swings started smoothing out. The violent chemistry that had defined this planet for so long began to steady itself into something new, something the rocks themselves would eventually describe as almost suspiciously calm. That settling did not happen overnight either. It took a few 100 million more years of quiet adjustment before the planet truly found the long even rhythm we started with earlier tonight, the one that would eventually stretch across an entire 1 billion years without a single dramatic chapter. Picture that recovering world for a moment if you can. Storms of ash and steam finally giving way to ordinary weather. Oceans once poisoned and then frozen solid, settling into a rhythm calm enough that waves could simply lap against stone again without anything underneath them changing overnight. A planet in every sense learning how to exhale. But you can already feel the next chapter gathering just past the edge of this one, can you not? After fire, after ice, after a mass extinction, nobody was even alive to name this exhausted, transformed planet was finally ready to catch its breath. And somewhere out on the horizon of that recovering world, pieces of drifting land, scattered fragments that had spent this entire violent stretch wandering the globe alone, were already beginning to inch toward one another, slowly, patiently, like old friends separated for far too long, finally finding their way back to the same familiar table. Hold on to that picture for a second, the one we ended on. Scattered pieces of land drifting alone across a healing planet, slowly turning toward each other for the first time, in longer than any of us could ever properly measure. Now let it actually happen. Over the following few 100 million years, something extraordinary took place so slowly that nobody watching it, if anyone had been capable of watching anything at all, would have noticed a single day of it happening. Land masses that had spent this entire planet's history wandering separately, bumping into nothing but ocean, finally began colliding. Not violently, not all at once, but the way two crowds might slowly merge at the edges of a gathering, first touching, then pressing, then locking together for good. Where they met, the ground itself buckled upward into mountain ranges taller than anything walking this earth today will ever get to climb, ranges that have since eroded down to nothing but the low ancient hills and buried bedrock most people now drive straight over without a second thought. If you could have watched this from high above across the full stretch of those hundreds of millions of years, it would have looked less like an event and more like breathing one impossibly slow inhale. Coastlines drawing closer together, ocean floor disappearing beneath advancing edges of rock, decade folding quietly into decade, century into century, until entire oceans that had separated these land masses for the whole of Earth's history simply were not there anymore. No sound announced any of it. No single afternoon marked the moment where two continents finally touched. It simply happened the way the tide comes, in the way you fall asleep without ever being able to name the exact second it occurred. By roughly 1.8 billion years ago, this process had finished. And for what many geologists now consider the very first time in this planet's entire 4.5 billion year history, nearly all of its scattered continental crust sat locked together in a single connected landmass. Think about that phrase again for a moment. The very first time. Not the first time in recent memory, not the first time in 100 million years. The first time full stop since this planet formed out of dust and collision, that its land finally fully came home to itself. Scientists gave this ancient supercontinent a name, though it turns out the naming itself became its own small, quiet argument, one that has apparently never fully been settled. Back in the late 1990s, a geologist named Paul Hoffman proposed calling it Nuna, borrowing a word from Inuktitut, the language of Inuit communities across the Arctic, roughly translating to land bordering the northern seas. It felt fitting. Much of the earliest evidence for this ancient landmass came from rock formations across the Canadian Arctic and Greenland, places about as far north as solid ground gets. A few years later, in the early 2000s, a different pair of researchers, John Rogers and a colleague, proposed an entirely different name, Columbia, after finding matching ancient rock formations connecting the state of Washington, right here in the United States, to a region on the completely opposite side of the modern globe in eastern India. Two names, two teams, two research papers, both describing what is essentially the same lost continent. And more than 20 years later, geologists are still in journal articles quietly debating which name deserves to win. I happen to find that oddly comforting. Even something as enormous as an entire vanished continent still comes down to two people who could not quite agree on what to call it. Here is a question worth sitting with while we are on the subject. How on earth does anyone figure any of this out? How do you look at a modern map at Washington State and eastern India, separated today by an entire ocean and half a planet, and conclude they were once pressed against each other? The answer involves something almost poetic if you ask me. When certain kinds of rock form, particularly rock that cools down from melted lava, tiny mineral grains inside it lock into place, and as they do, they align themselves with Earth's magnetic field at that exact moment, the way a compass needle settles toward north. Once the rock finishes cooling, that alignment freezes permanently in place, a tiny fossilized compass needle, pointing toward wherever north happened to be on that particular patch of ground on that particular day over 1 billion years ago. Multiply that single frozen compass needle across thousands of rock samples collected from every continent on Earth, and you can slowly, patiently reconstruct where every single piece of land used to sit long before anyone existed to draw a map of it. Picture a geologist somewhere out in a rocky, sunburned field in Western Australia, chipping a fist-sized sample out of a hillside that has not moved in over 1 billion years, labeling it carefully, flying it back to a laboratory, and feeding it into a machine sensitive enough to detect the whisper of magnetism still locked inside. Then picture that same patient work repeated across Canada, across Scandinavia, across the red desert interior of Australia, across the hills of eastern India. Decade after decade, one research career passed quietly along to the next. That is not a single discovery. That is closer to an entire multi-generational relay race still being run today by people who will likely never see the full finished picture in their own lifetime and who keep running anyway. It is not a perfect science. Researchers who work on these reconstructions will tell you themselves that plenty of the picture remains honestly uncertain. Entire chunks of this ancient supercontinent shift position from one published study to the next, depending on whose data you trust most. If you ever see a tidy, confident-looking illustration of this ancient world online, one single definitive shape, treat it a little skeptically. The honest version of this story is closer to an unfinished jigsaw puzzle, one where most of the border pieces are in place, but plenty of the middle is still educated guesswork. Still, the broad outline holds up remarkably well across almost every version of the reconstruction. Somewhere at the heart of this ancient supercontinent sat the old hard rock now buried beneath much of Canada, the kind of deep, stable stone geologists call a craton rock, so ancient it had already been sitting quietly for over 1 billion years before this whole assembly even began. Pressed against it sat what would eventually become Scandinavia and a portion of what we now call Siberia. Farther along the edges, fragments that would one day drift apart into Australia, into pieces of southern Africa, into slivers of what is now India, all locked together, at least for a while, into one enormous connected shape. To put a rough size on it, most reconstructions suggest this single landmass would have dwarfed modern Asia, the largest continent we currently have, stretching across a distance wide enough that walking from one coastline to the opposite one at a steady human pace could have taken the better part of a year, assuming there had been anyone around yet to attempt the walk and any reason at all to try. If you're watching this from somewhere in North America tonight, here is a strange thought to fall asleep on. Some of the bedrock underneath your own house buried far below the basement, the pipes, the foundation may very well be an actual surviving fragment of this exact ancient supercontinent rock that has been sitting quietly in roughly the same place for well over 1 billion years, long before there was a country, a language, or a single human being anywhere on the planet to name it. Living anywhere near the outer edge of this joined landmass would have felt strange but survivable. Ordinary coastline, ordinary tide, ordinary rhythm of waves. But picture instead standing at the true center of it, thousands of miles from the nearest ocean in every single direction. Can you imagine that kind of distance from water? Modern continents are simply too small to fully recreate what that would have felt like, but geologists who study ancient supercontinents generally agree on the pattern. Deep interior regions cut off from the moisture and moderating warmth an ocean normally provides tend to swing brutally between extremes, scorching dry heat for what would have been called summer and a hard bitter cold for whatever passed as winter, with almost no rain reaching that far inland to soften either one. An entire vast heartland of this ancient world may have existed as something near permanent desert, silent, cracked, and largely lifeless, even while the coastlines ringing its outer edge stayed relatively mild. Once this landmass finally came together, something else happened, something that helps explain a piece of the mystery we have been circling around all night. Large connected continents behave differently than scattered ones. Underneath the surface, heat is constantly rising up from deep within the planet, and normally that heat helps drive the slow churn of plate tectonics plates, sliding, colliding, sinking back down into the mantle in an endless gradual cycle. But a single enormous landmass acts almost like a thick blanket thrown over that rising heat, trapping it below, instead of letting it escape efficiently through numerous smaller plate edges. With less heat escaping, the whole system slows down, fewer collisions, fewer new mountain ranges, less of almost everything that normally keeps a planet's surface restless. In a very real physical sense, this coming together is part of why the world you've been listening to me describe all night finally went quiet. Some researchers who study this period even suspect that heat quietly building underneath that blanket for hundreds of millions of years was never actually gone. It was only ever being stored patiently the way a kettle left on a low flame will eventually inevitably start to sing. This particular supercontinent would hold together for an extraordinarily long stretch of time, but nothing built from trapped rising heat stays perfectly still forever. That particular chapter, though, belongs later in tonight's journey, not here. There is another quieter consequence too, one that touches directly on the story of life itself. Picture a coastline for a moment, the specific narrow strip where land meets shallow ocean water, sunlit, nutrient-rich, exactly the kind of place where early simple life tends to do best. Now imagine dozens of separate continents, each with its own coastline, all merging into a single connected landmass instead. Fewer total continents means dramatically less total coastline, and less coastline means fewer of those shallow, sunlit, nutrient-rich shelves where life could really stretch its legs, so to speak. It is a small, physical detail with an outsized consequence. Have you ever noticed how a room full of separate small conversations can feel more alive, more chaotic, more interesting than one enormous group all gathered around a single quiet table? Life on this planet, in a strange way, was about to experience something similar, whatever thin. Patient mats of simple organisms had been quietly spreading along countless separate coastlines, now found themselves squeezed onto far fewer of them, sharing space-sharing nutrients, growing no faster, no bolder than they absolutely had to. I think there is something worth sitting with in this particular chapter of the story, something a little different from anything we have talked about tonight so far. We live in a culture that tends to celebrate constant movement. New cities, new jobs, new versions of ourselves arriving one after another, almost as proof that we are still growing. Staying in one place, staying with the same people, the same routine, the same quiet life for years on end sometimes gets quietly treated like settling, like giving up on something bigger. But this ancient supercontinent tells a slightly different story. It's coming together, it's staying together, its refusal to keep drifting apart for hundreds of millions of years was not a failure of ambition. It was the exact condition the rest of this story needed in order to happen at all. I think about that sometimes when I look back at the quietest years of my own life, the ones that felt while I was living through them like nothing was happening at all. No big trip, no dramatic change, just the same street, the same small routines day after day. It rarely feels like progress while it is happening. But looking back, those were usually the years something was actually being built underneath the surface, even if I could not have named what at the time. Sometimes the version of yourself still being built needs exactly this. Not movement, just enough stillness to finally take root. And take root it did. For hundreds of millions of years, this vast joined landmass simply sat there largely unchanged, anchoring an entire planet into the long, steady rhythm we've been circling ever since the beginning of tonight's story. Mountains that had risen during its formation slowly wore down under nothing but rain and moving air, one grain of sand at a time, with nothing dramatic enough happening nearby to interrupt them. But something else, something quieter still was happening out beyond that ancient shoreline hidden beneath the surface of the water itself. All this time we have been describing an ocean without really looking closely at what filled it, what colour it carried, what strange chemistry moved silently through its depths, while the continents above it settled into their long patient stillness. That water was not simply sitting there empty and clear, waiting politely for something interesting to happen on land. It was doing something far stranger than that, something almost nobody pictures correctly the first time they hear it described. So let's slip beneath that calm surface now gently, the way you might lower yourself into a warm bath at the very end of a long day, and take a slow, careful look at exactly what that ancient ocean had quietly become, while everything above it stayed so remarkably, deceptively still. The first thing you would notice drifting down through those ancient waters is how ordinary everything feels at first. Sunlight breaking apart into pale, wavering ribbons above you. A thin, breathable layer near the surface carrying just enough oxygen to remind you of home. For the first stretch of your descent, this could almost pass for any ocean anywhere on any given afternoon. Small drifting shapes catch the light for a moment before disappearing again. Colonies of simple, single-celled life going about their business exactly the way they had for longer than you could ever comfortably picture. Then somewhere below that comfortable upper layer, the water changes. It is subtle at first. A faint shift in temperature maybe, a strange mineral heaviness settling into the water around you, and then unmistakably a smell finds you even underwater somehow, the way certain smells seem to reach you before you can explain how. Rotten eggs. Sharp, unmistakable, the exact same smell you might remember from a natural hot spring on some family vacation, or the sulphur smell that lingers near certain volcanic hillsides. Except here it is not coming from one small spring tucked into a hillside. It is coming from the ocean itself, filling an entire hidden layer of water that most people even now have never once heard mentioned. Geochemists have a name for this layer and a name for the whole strange ocean it belonged to. They call it the Canfield Ocean, after a researcher named Donald Canfield, who first proposed the idea in a paper published in the late 1990s. Before his work, most scientists assumed that once oxygen filled the atmosphere, following everything we talked about earlier tonight, the entire ocean must have gradually oxygenated to top to bottom in a fairly straightforward way. Canfield looked at the same ancient rocks everyone else had been studying and noticed something that did not quite fit that tidy story. The chemistry preserved in stone from this era did not look like an ocean quietly filling up with oxygen. It looked like an ocean quietly filling up with sulphur instead. Here is roughly how the picture came together. Rain and rivers moving across newly oxygen-exposed rock on land slowly wash sulfate, a sulphur-rich mineral, down into the sea in far greater quantities than ever before. Deep below the surface, away from sunlight, certain bacteria discovered they could use that sulfate the way we might use oxygen, breathing it in, so to speak, and breathing out hydrogen sulfide as waste. That gas is exactly the one responsible for the rotten egg smell you may already know from somewhere in your own life. Layer by layer, century by century, this hydrogen sulfide built up in the mid-depths of the ocean, spreading outward from productive coastlines into a vast, invisible, toxic middle layer sitting quietly beneath a thin, ordinary-looking surface. Have you ever met someone who seemed completely fine on the surface? Easy conversation, easy smile, and only much later did you learn what was actually happening underneath. This ancient ocean strikes me as something similar to that. Calm on top, complicated the moment you looked closer. And here is where the story turns almost beautiful in its own strange way. That toxic, sulfur-rich layer was not simply empty, waiting to poison anything unlucky enough to swim through it. Certain organisms had already figured out how to turn it into an opportunity instead. Along shallow coastlines, exactly where sunlight still reached down into that sulfide-rich water, entire communities of bacteria evolved a completely different kind of photosynthesis. Nothing like the oxygen-producing kind cyanobacteria had already mastered. These organisms, now generally grouped as green and purple sulfur bacteria, learned to use hydrogen sulfide itself as their raw material, the way ordinary plants use water, releasing not oxygen but tiny grains of pure sulfur as their leftover waste. Picture that shoreline for a moment if you can. Somewhere near the surface, thin veils of green-tinted water, coloured by countless microscopic organisms feeding on sulfide and sunlight together. A little deeper, patches shifting toward a strange dusty purple, almost the colour of a healing bruise or a sky about 20 minutes after sunset. Some researchers studying this period have half-seriously nicknamed it Earth's Purple Phase, imagining coastlines tinted in shades most of us have never associated with an ocean before. I find something quietly stunning about that image. An entire coastline glowing faintly green and violet powered by chemistry most of us go our whole lives never once considering. How do scientists actually know any of this, given that none of it survived as anything you could hold in your hand? The answer involves chemical traces almost too small to imagine faint fingerprints left behind by these ancient organisms preserved for over 1 billion years inside the specific arrangement of molecules found in certain layers of dark ancient shale. Specialized pigments unique to these particular sulfur-loving bacteria break down over time into stable compounds that survive essentially forever, quietly waiting inside solid rock until a researcher with the right equipment finally goes looking for them. Finding one of these chemical fingerprints buried inside a billion-year-old rock sample is about as near as modern science gets to proving a colour existed long after every witness to that colour is gone. There is something almost detective-like about that entire process if you think about it long enough. A researcher decades from now or decades ago, splitting open a slab of ordinary-looking grey rock, pulled from some unremarkable hillside running it, through careful chemical analysis, and slowly realizing that the exact molecular signature staring back at them could only have come from a specific family of bacteria that needs both sunlight and hydrogen sulfide to survive. No sunlight and hydrogen sulfide occurring together anywhere on the modern surface of this planet, except deep inside a handful of very specific, very stagnant bodies of water. Put those two requirements together and that single slab of rock quietly confirms something enormous, an entire coastline tinted green and purple, sitting exactly where this piece of stone was pulled from over 1 billion years ago. Now here is the part of the story that connects everything we have circled around tonight into something a little more complete. Hydrogen sulfide is not simply unpleasant to smell. It is actively seriously toxic, and not only to us. It interferes directly with the way complex cells process oxygen, for energy essentially jamming the machinery most animals rely on to breathe at all, through a mechanism disturbingly similar to certain classic poisons. Modern toxicologists actually place it in roughly the same category of danger as cyanide, since both work by quietly shutting down the same tiny essential engine inside almost every complex cell, the one responsible for turning oxygen into usable energy in the first place. For any early complex organism attempting to evolve during this stretch of Earth's history, drifting into the wrong depth of ocean water could have been fatal, not from a lack of oxygen exactly, but from an active chemical assault the moment oxygen tried to do its job. This, more than almost anything else we've discussed tonight, may help explain why complicated life stayed locked in place for so unbelievably long. It was not simply that conditions were dull or uneventful. Significant portions of the ocean itself were actively hostile, a toxic middle layer sitting between a thin, breathable surface and a deep, ancient floor effectively squeezing anything trying to evolve into complexity onto a narrow, precarious shelf near the very top of the water. There is a second, quieter effect worth mentioning too, one easy to miss the first time you hear this story. Hydrogen sulfide does not just poison complex cells directly, it also reacts with certain trace metals dissolved in seawater metals with names like molybdenum and copper, quietly pulling them out of circulation and locking them into solid mineral form on the seafloor instead. That might sound like a minor chemistry detail, but those exact metals happen to be essential ingredients. Certain organisms need to pull nitrogen out of the water and turn it into usable nutrients, a process much of the ocean's productivity has always depended on. Strip those metals away, and you do not just poison the water, you quietly starve it too. Removing key ingredients life would have needed to grow bolder, faster, more ambitious. It becomes a strange self-reinforcing loop, toxicity and scarcity feeding each other, helping hold an entire planet's biology in place for the better part of 1 billion years. I want to pause here and offer a small honest correction because I think the real version of this story deserves it. For a long time after Canfield first proposed this idea, plenty of scientists and plenty of documentaries since described this entire ocean as one uniform sulfur-choked nightmare from pole to pole. More recent research complicates that picture in a way I actually find more interesting, not less. Newer studies using different chemical traces pulled from ancient sediments suggest these toxic sulfidic zones were likely patchy rather than universal, concentrated most heavily along particularly productive coastlines, while other stretches of deep ocean may have stayed closer to the older iron-rich chemistry we talked about earlier tonight. Some researchers have even pointed out a kind of built-in limit to how widespread this toxic chemistry could ever become, since the very organisms producing hydrogen sulfide depend on a steady supply of decaying matter, drifting down from productive surface waters above them, and those same trace metal shortages we just talked about would have eventually throttled that productivity too. The honest picture is less a single villain, and more a shifting, uneven mosaic, dangerous in some places, merely strange in others, and this nuance rarely makes it into the tidy single-sentence version of the story most people repeat. If you want a living example of something similar to this, you barely have to leave the modern map to find one. The Black Sea tucked between Eastern Europe and the edge of Asia still behaves this way today right now while you are listening to this. Its surface waters support ordinary fish, ordinary boats, ordinary summer holidays along its coastline. But dive down past a few hundred feet and the water itself turns anoxic and sulfidic dense, with hydrogen sulfide essentially lifeless to anything requiring oxygen to survive. Entire ancient shipwrecks, some over 1,000 years old, sit almost perfectly preserved down there today, because the very same toxic chemistry that would kill you also happens to stop the ordinary bacteria responsible for wood slowly rotting away. A research team surveying those depths a few years back photographed one particular wooden trading vessel, so intact, mast, still standing oars, still roughly in place, that some researchers on the project believe it may be among the oldest fully intact ships anyone has ever found, still resting exactly where it sank over 2,000 years ago. In a strange sense, a small living fragment of that ancient billion-year-old ocean chemistry never actually left us. It is still sitting quietly at the bottom of one particular sea right now tonight, while most of the world sails calmly across its surface without a second thought. I keep coming back to that layered image, if I am honest with you. A calm, ordinary surface, a complicated, occasionally toxic layer underneath doing quiet damage nobody above the waterline can see. And underneath even that something older and steadier still. I do not think it is much of a stretch to notice how closely that mirrors certain seasons of an actual human life. The version of yourself you show at work at a family dinner in the comments under a photo, calm put together, entirely normal on the surface. And underneath that, sometimes something heavier moving quietly along invisible to almost everyone except maybe the one or two people who know how to look past the surface layer entirely. Have you ever carried something like that? Something nobody around you could quite see, while everything on the surface looked completely fine? I do not think the lesson here is that depths are something to fear. I think it might be closer to the opposite. This ancient sulfur-rich ocean, dangerous as parts of it clearly were, is also the same body of water that would eventually patiently finish incubating everything required for complex life to exist at all. Sometimes the most important work truly does happen in the parts of us or the parts of a planet that nobody else gets to see directly. And sometimes the fact that something looks calm and unremarkable from the outside is not evidence that nothing difficult is happening. It might simply mean the difficult part has not finished yet. For now, though, up near that thin sunlit surface, life continued on largely unaware of any of this, doing exactly what it had already been doing for well over 1 billion years in exactly the same patient, unhurried way. Small, simple, endlessly repetitive on the surface at least. It is worth spending a little time inside that particular kind of patience next, because once you know what was quietly happening just a little further down in that hidden, purple layer, nobody above the water ever saw, the so-called sameness up above starts to look a good deal less empty than it first appears. There is a version of this story where nothing at all seems to be happening near that sunlit surface, and there is the version we now understand a little better where an entire complicated world was quietly humming along just beneath it, near enough to touch, and far enough away that almost nothing up above ever noticed. Let's stay right there a moment longer near that quiet sunlit surface before we drift anywhere else tonight. Because if you had actually been able to visit this planet during any random afternoon inside that billion-year stretch, and you went looking for something dramatic to watch, you would have come away thoroughly disappointed. No creature chasing another creature. No dramatic battle for territory. No single moment worth pointing a camera at if cameras had existed. Just an endless, shallow, sunlit shoreline covered in something that from a distance would have looked almost like a stain on the rock. A thin, slippery, faintly slick coating stretching for miles in every direction, doing absolutely nothing that looked from the outside like it deserved a second glance. If this billion-year stretch of Earth's history had a highlight reel, it would mostly just be footage of the same shoreline on repeat, for what felt like forever, the kind of video most viewers would scroll straight past within about 4 seconds. Look near enough, though, and that so-called nothing turns out to be one of the most quietly organized things this planet has ever produced. Biologists call these thin-layered coatings microbial mats, and if you have never given one much thought before, that is completely understandable. since most of us walk past their modern descendants without noticing them at all, along the edges of ponds, tide pools, the slick green coating on a rock near a slow-moving stream. But strip away the assumption that thin automatically means simple, and something far more interesting starts to show up. A single mat, sometimes barely thicker than a stack of a few playing cards, can contain distinct working layers stacked one directly on top of the other, each layer doing an entirely different job. Near the very top, where sunlight lands first, you would find organisms busy producing oxygen. Just beneath them, a layer surviving on leftover light too weak or too filtered for the top layer to use. Below that, organisms feeding on whatever chemical waste the layers above them happen to produce, and beneath even that, in the darkest, oxygen-starved bottom layer, an entirely separate community living off sulfur compounds seeping up from the mud, underneath the same kind of chemistry we spent so long exploring a little earlier tonight, just tucked here into a space thinner than your smallest finger. It is less like a stain and much more like an apartment building, every floor doing its own specialized work, quietly dependent on every floor around it, none of them able to survive particularly long without the others. Zoom out far enough, and the whole arrangement starts to look less like biology and more like an economy, a self-contained, endlessly patient trading system, where oxygen produced upstairs becomes fuel for a downstairs neighbor, and waste produced downstairs becomes raw material for someone else entirely. Nothing here needed a manager, nothing needed instructions. It simply settled generation after generation into the single, most efficient shape available to it, and then it kept that shape largely unchanged for a length of time that makes recorded human history look like the space between two heartbeats. What strikes me most thinking about it now is how completely this entire system balanced itself without anything resembling a plan. Nobody negotiated which layer got which resource. Nobody voted on how much oxygen the top layer should share with the layer just beneath it. And yet, through nothing more than plain trial and error repeated across an almost incomprehensible number of individual lives, this arrangement settled into something remarkably near equilibrium, a give-and-take precise enough that geologists can still trace its steady, even signature in rock laid down over 1 billion years ago. Sometimes the most stable systems in existence are not the ones somebody carefully designed. They are the ones patient enough to simply keep adjusting in tiny increments until nothing about them needed adjusting anymore. Here is a question worth sitting with while you picture that. How many of us looking at something thin, slick and unremarkable would ever guess it was secretly this organized underneath? There is something else worth noticing here too, something that quietly complicates the entire idea of this 1 billion years being uneventful. Individually, the organisms making up these mats were living remarkably fast lives. Certain simple bacteria today under good conditions can double their entire population in as little as 20 minutes, which means an organism born at the very start of an ordinary afternoon could by dinner time have given rise to generations numbering in the trillions. Multiply that kind of pace across an entire 1 billion years, and you're not looking at a handful of ancient organisms slowly, cautiously making their way through deep time. You're looking at more individual life and death, more individual generations than most of us could ever comfortably hold in our heads. At once an almost unimaginable amount of activity, happening at a scale too small and too fast for the fossil record to ever fully capture. Consider it this way for a moment. If you tried to count human generations across the entire span of recorded civilization, from the very first written records right up through tonight, you would land somewhere around a few hundred, maybe pushing toward a couple thousand, if you stretch the definition of civilization as far back as it will comfortably go. A single patch of these ancient microbial mats could rack up that same number of generations in considerably less than a single calendar year. Multiply that patience across 1 billion years, and the number of individual lives lived and lost inside that supposedly boring stretch stops feeling small at all. It starts to feel closer to incomprehensible. And yet across every single one of those uncountable generations, the shape of the whole system barely moved. Parents looked essentially identical to their offspring, who looked essentially identical to their offspring after that, an unbroken chain of near-perfect copies stretching back further than any family tree any of us could ever hope to trace. So here is the real puzzle worth pausing on. If individual life was moving that quickly, constantly reproducing, constantly dying, constantly starting over, why did the overall picture stay so stubbornly the same for so unbelievably long? Why did none of that frantic minute-by-minute activity ever seem to add up to anything looking from a distance like meaningful change? I think a lot of us grew up with a slightly misleading picture of how evolution is supposed to work, honestly myself included, before I properly looked into it. You have probably seen that famous illustration somewhere, a hunched ape-like figure on the far left, gradually straightening up step by step, until an upright human strides confidently off the right edge of the page. It is everywhere, printed on shirts turned into jokes, treated almost like an unofficial logo for evolution itself. The trouble is, biologists have spent decades quietly pointing out that this image gets the entire idea backward. Evolution was never marching toward anything. It does not reward complexity for its own sake, and it certainly is not aiming toward us or toward anything else as some kind of final destination. It simply rewards whatever survives and reproduces successfully in the conditions actually present at the time. Here is a small detail I find quietly satisfying. The very first sketch Charles Darwin ever made of this entire concept, scribbled into a private notebook back in the 1830s, was not a straight line or a ladder at all. It was a tree branches splitting off in every direction, some short, some impossibly long, with 2 small words written above it simply, I think. No single branch sits above any other branch on that page. No branch is drawn as more finished, more advanced, or more important than the branches around it. It was already the right picture from the very beginning, and somewhere along the way, popular imagination quietly swapped that branching tree for a tidy single file line marching confidently forward. These simple mat-forming organisms sit on one of the oldest, sturdiest branches on that entire tree, not lagging behind the rest of it, not waiting their turn to catch up to something better. And by that particular measure, these simple mat-forming organisms were not failing to evolve during this stretch of time. They were succeeding at it spectacularly over and over again for an entire 1 billion years straight. Their basic design already solved every problem their environment was actually asking them to solve. Grab sunlight, grab nutrients, reproduce quickly, repeat. When something already works this well, evolution tends to leave well enough alone, favouring only small refinements instead of any dramatic reinvention. There was no invisible pressure nudging these organisms toward becoming something bigger or more complicated, because nothing about their world was demanding it of them yet. You can still find something like a living window into this exact pattern today if you know where to look for it. Deep in the frozen valleys of Antarctica, in a handful of ice-covered lakes that stay liquid year-round, underneath a thick permanent ceiling of ice, researchers have found microbial mats living in conditions that echo in strikingly similar ways the ancient world we've been describing tonight. Cut off from storms, from waves, from almost any outside disturbance, these mats grow in slow, careful layers for years at a time, largely undisturbed, essentially isolated laboratories of exactly the kind of patient-layered life that once covered enormous stretches of this planet's ancient coastlines. Some of these lake mats grow into strange tower-shaped formations rising a foot or more off the lake floor over the course of many decades, one impossibly thin layer added at a time, a little like a candle. No one is watching, slowly, patiently building itself taller. Scientists studying them describe the experience as something like walking through a working model of deep time itself, a place where the ordinary rules of a rushed modern world simply do not apply. I want to sit with something here for a moment because I think this particular part of the story deserves more than a passing mention. We live in a culture that measures worth almost entirely through visible change. New job titles, new skills publicly announced, noticeable growth, ideally with some kind of before and after to show for it. And against that backdrop, doing the exact same competent, quiet work, day after day, year after year, without any dramatic milestone attached to it, can start to feel a little like failure, even when the work itself is going beautifully. Have you ever kept doing something well, quietly, faithfully for a long stretch of time, without anyone around you really noticing or acknowledging it? I think about the people who show up for that kind of work anyway. Someone who has shown up for the same difficult job for 15 years, steady, dependable, never once making headlines for it. A parent repeating the same small routines every single morning, the same lunches, packed the same reminders, given nothing about it, ever photographed or posted anywhere. A friend who checks in on you the same quiet way year after year, never asking for credit, rarely even mentioned when people describe what has kept them going. None of that looks like a highlight reel. Almost none of it would survive being turned into a headline. But it is very often the exact thing holding an entire life together, the same way these mats, unnoticed and unphotographed for 1 billion years, were quietly holding an entire planet together. If you happen to be someone doing exactly that kind of unglamorous, faithful work right now, in whatever corner of your own life needs it most, I hope some small part of tonight's story feels like it was quietly written for you too. These simple organisms never once doubted themselves over this. They were not waiting around wondering if they should be doing something bigger, something more impressive, something worth writing home about. They were simply completely, extraordinarily good at exactly what they were already doing, and being good at exactly what you are doing consistently for a very long time is its own entirely legitimate form of success. It does not always look like progress from the outside. It rarely makes for dramatic footage. But an entire planet's worth of oxygen, an entire planet's worth of chemical balance, was being quietly maintained this whole time by creatures that never once needed to become something else in order to matter. Still, something was different underneath all of this. Something easy to miss if you are only watching the surface of that shoreline and not paying careful enough attention to a few unusually patient stragglers quietly doing something slightly stranger than all their neighbours. While the vast majority of this world's biology kept perfecting the exact same simple design, refining it, repeating it, mastering it a little further. With each passing century, one small, easily overlooked group of organisms was doing something entirely different, something that had never quite happened on this planet before. It would take an almost unbearably long time for anyone, anything to notice, since whatever was happening inside these particular cells left almost no visible trace at first, nothing large enough to fossilize clearly, nothing dramatic enough to interrupt a single one of these endless repeating afternoons along the shoreline. And yet tucked inside some of these ordinary-looking cells, something was quietly being rearranged from the inside, a kind of internal reorganization far stranger and far more consequential than anything sitting on the outside of that cell could have hinted at. Once that quiet rearrangement finally did happen, everything about how complicated life could eventually become on this planet started to shift, gradually and visibly, one single cell at a time, long before anything on the surface gave the slightest indication that anything at all had changed. Somewhere along that same unremarkable coastline, we've been circling all night on an afternoon that looked exactly like every afternoon before it. One small cell did something no cell on this planet had ever managed before. Sunlight fell across the water the same way it always had. The same thin layered mats went on quietly doing their same patient work along the shallows. Nothing about the sky, the tide, or the temperature gave any hint that this particular afternoon deserved to be remembered differently than the billion or so afternoons that had already come before it. It swallowed another cell whole, and instead of digesting it the way you might expect, it kept it alive. Nobody can point to the actual day this happened or the specific patch of ancient shoreline where it took place. There was no witness, no sudden change visible from the outside, nothing that would have looked to anyone standing nearby like anything worth remembering. And yet biologists now consider this single quiet, accidental partnership one of the 2 or 3 most important events in the entire history of life on this planet, arguably more consequential than almost anything we have talked about so far tonight. Here is roughly what scientists believe happened pieced together from evidence buried inside nearly every living cell on Earth today, including yours. A larger simple cell, the kind that had already been drifting through these oceans for well over 1 billion years, by this point somehow absorbed a smaller cell, a different kind of ancient bacterium, one that had already mastered a particular trick. That smaller bacterium knew how to burn oxygen for fuel, extraordinarily efficiently turning it into far more usable energy than the larger cell had ever been capable of producing on its own. Normally, an encounter like this would end with one simple outcome. The bigger cell eats, the smaller one breaks it down and moves on. This time, for reasons still not entirely understood, that did not happen. The smaller cell survived, tucked safely inside its new host, and somewhere along the way the 2 of them stopped being predator and prey entirely and started being something else. Partners. That surviving bacterium eventually became what we now call the mitochondrion, the small oval structure sitting inside almost every complex cell on the planet, quietly converting oxygen into usable energy right now inside you as you listen to this. Think about that for just a second if you can, without letting it keep you awake longer than tonight's story already will. Somewhere inside nearly every one of your own cells right now, there are structures descended directly from an independent, free-living organism that made a similar accidental journey well over 1 billion years ago along a shoreline neither of us will ever see. You're not simply one living thing. In a very real biological sense, you're a walking partnership 1 billion years deep. And once that partnership took hold back on that ordinary, unremarkable afternoon, it changed absolutely everything about what life on this planet was capable of becoming. I want to pause here and tell you about the person who first convinced the scientific world to take this idea seriously, because her story is honestly one of my favourite parts of this entire chapter, and it deserves a few minutes on its own. In the middle of the 1960s, a young biologist named Lynn Margulis, still in her 20s, sat down and wrote a lengthy paper, laying out exactly this theory that certain structures inside complex cells were not originally part of the cell at all, but were once free-living bacteria swallowed and kept alive rather than digested. She sent it out to be published. It was rejected, then rejected again. By the time it finally found a home in a journal willing to print it, Margulis had reportedly been turned down by around 15 separate scientific publications. One grant reviewer evaluating her work around that same period apparently summarized their feedback in 3 blunt words, calling her research quite simply worthless. For roughly another decade after her paper finally appeared in print, Most of the scientific community treated the whole idea as a curiosity at best and outright nonsense at worst. Picture that for a moment, if you would. A young researcher not yet 30 years old carrying around an idea that would eventually be taught to essentially every biology student on the planet, and having to sit through meeting after meeting, rejection after rejection, listening to more established, more credentialed voices explain patiently, condescendingly exactly why she must be mistaken. Can you imagine holding on to an idea that firmly for that long while person after person in your own field tells you directly to your face that you are wrong? Margulis did not back down. She kept teaching, kept publishing, kept quietly building her case one paper at a time, while an entire field of specialists remained largely unconvinced around her. Then through the 1970s and into the 1980s something shifted. Genetic testing improved to the point where scientists could finally look directly inside a mitochondrion and check its deepest chemistry against her prediction. What they found matched her theory almost perfectly. Mitochondria, it turned out, carry their own small ring of genetic material entirely separate from the main genetic material sitting inside the rest of the cell and shaped like a simple loop, exactly the way genetic material sits inside an ordinary bacterium, and nothing like the long organized strands found everywhere else inside a complex cell. Mitochondria even divide on their own schedule, splitting in two, the same simple way bacteria do, largely independent of when the rest of the cell decides to divide. There is one more piece of evidence I happen to find almost charming in its own quiet way. Every mitochondrion sitting inside your own cells right now is wrapped in two separate membranes, one nested neatly inside the other, rather than the single membrane most structures inside a cell tend to have. Biologists eventually realize this makes perfect sense if the story is true. The inner membrane once belonged to that original independent bacterium, its own outer skin from back when it was still living entirely on its own. The outer membrane is essentially a leftover bubble formed at the exact moment the larger cell first folded itself around that bacterium and swallowed it whole. In other words, if you know what you're looking for, that ancient moment of capture is still quite literally wrapped around the very structure, keeping your own body warm and running tonight. Every piece of evidence researchers could gather pointed toward the exact same conclusion Margulis had been quietly defending since her 20s. She had been right the entire time. By the time she passed away decades later, Margulis had been elected to the National Academy of Sciences and had personally received the National Medal of Science from a sitting president, presented to her at a ceremony most of the same academic world that once dismissed her work would have watched with quiet approval. She spent the later decades of her career pushing the same underlying idea into new, sometimes still controversial territory, arguing that cooperation between organisms deserved just as much attention from biologists as competition, had always received an argument plenty of her colleagues still debate today. An idea that 15 journals once refused to print eventually became one of the settled foundational facts every single biology student on Earth now learns before they even reach college. I do not think it is much of a stretch to notice how closely her own story mirrors the story she was trying to tell, a quiet, patient truth dismissed again and again, finally recognized for exactly what it had been all along. Here is something I find worth sitting with, something a little different from the lessons we've pulled out of tonight's story so far. For most of human history, we have told the story of evolution almost entirely through combat teeth, claws, competition, survival of whichever creature outfights all the others. Margulis, more than almost anyone before her, insisted on a different possibility. Some of the biggest leaps in the history of life did not come from combat at all. They came from cooperation, two entirely different organisms finding a way to need each other more than they needed to destroy each other. Have you ever had a partnership like that in your own life, something that started almost by accident, maybe even a little uncomfortably at first, and slowly, quietly became one of the most important relationships you have. A business partner you almost did not choose, a roommate who became family, a marriage that began as something far less certain than it eventually turned into. None of those relationships announce themselves as historic on day one. Almost none of them do. They simply survive one ordinary season after another, quietly proving their worth long after the initial uncertain beginning has been mostly forgotten. Now, why did any of this actually matter beyond simply being a fascinating piece of biological history? Here is the part that ties everything else we've discussed tonight together. A simple cell working entirely on its own, without this borrowed source of energy, can only support a fairly small, modest genetic instruction set before it runs out of fuel to keep everything running. But a cell with mitochondria on board, sometimes hundreds of them working round the clock, suddenly has access to a remarkably staggering surplus of usable energy, several times more than its old self could ever have generated alone. That surplus is what eventually allowed cells to afford something they never could have afforded before: larger genomes, more specialized internal structures, entirely new kinds of biological complexity that a simple energy-poor cell simply could not have supported, no matter how many millions of years you gave it to try. So when did any of this actually leave a trace in the rock record? Here, honestly, the fossil evidence gets a little messier than I would like it to be, and I think you deserve the honest version rather than a tidy one. Some of the earliest possible eukaryotic fossils, strange spiral-shaped ribbons known as Gripania, first noticed in rock in Montana more than a century ago, show up in formations across Michigan, dated to somewhere near 1.9 billion years old. For a long time, that made Gripania a leading candidate for the oldest known eukaryote on the entire planet. But researchers still honestly disagree about what Gripania actually was. It might have been an early alga, an authentic eukaryote, the very kind of organism this whole partnership eventually made possible. It might instead have simply been an unusually large colony of ordinary bacteria spiraling into a shape that only looks complex from the outside. Multiple research teams have looked at the exact same spiral fossil and walked away with different conclusions. What almost everyone does agree on is this: by around 1.6 billion years ago, the fossil record starts showing something far less ambiguous. Tiny, hollow, spherical fossils with complicated, ornamented walls, unmistakably built by cells, organized in a way only a true eukaryote could manage. Researchers call these microfossils acritarchs, a word that essentially means of uncertain origin, since scientists still cannot always say exactly which branch of the tree of life produced any individual specimen. But the walls themselves, the intricate spikes, ridges and geometric patterns preserved on some of these tiny spheres, require a level of internal cellular scaffolding no simple bacterium has ever been shown capable of building. Whatever exactly these particular organisms were, something inside them was undeniably structurally new. Somewhere between that quiet, unwitnessed partnership and this later clearer fossil evidence, an entirely new category of life had firmly taken hold, even though almost nobody watching this planet's shoreline during those early centuries would have had any way of noticing it happening. I keep coming back to that particular gap, honestly, the gap between when something enormous actually begins and when the rest of the world finally has enough evidence to notice it clearly. It happened with the mitochondria hiding quietly inside an ordinary-looking cell for who knows how many centuries before anyone could prove it. It happened with Margulis herself sitting on an idea the scientific world was not ready to accept for almost 20 years. Some of the most important beginnings in this entire story, in any story, do not announce themselves. They simply happen quietly and wait patiently for the proof to eventually catch up. For now, though, this new kind of cell remained rare, tucked here and there along an otherwise unchanged prokaryote-dominated shoreline, still surrounded by the very same landmass, the very same restless ocean chemistry we have spent so much of tonight exploring. That landmass, remember, had been sitting largely still for a remarkably long stretch of time by this point, anchoring the whole planet into the long, even calm we started tonight's journey inside. But calm as we are about to find out was never quite as permanent as it looked from the surface. Underneath that same patient ground, quite literally something was already beginning to shift again, and this time the shift would not stay hidden nearly as long as this one just did. It started, as far as anyone can tell, not with a crack, but with a warming. Remember that trapped heat we talked about earlier tonight, quietly building underneath this joined landmass for hundreds of millions of years, the way a kettle left on a low flame will eventually inevitably start to sing. That heat never actually went anywhere. It simply waited, rising slowly through the deep mantle beneath the center of this ancient supercontinent patient, in a way almost nothing on the surface above it had any reason to notice. Then sometime around 1.5 billion years ago, give or take, that patience finally ran out. Deep beneath the middle of this vast joined landmass, columns of unusually hot rock began pushing upward from far below the kind of slow rising plume that takes millions of years to travel from the deep mantle to the underside of solid crust. Picture something like an enormous invisible flame burning steadily beneath a single spot on the map for longer than any human civilization has ever managed to survive, patiently softening the rock sitting directly above it. When that heat finally arrived, it did what heat under pressure always eventually does. It started to stretch things. The rock directly above these rising plumes began thinning almost imperceptibly, at first valleys sinking a little lower than the land around them, faint cracks appearing in stone that had sat completely undisturbed for the better part of 1 billion years. Nobody standing on that ground, if anyone had been standing there at all, would have felt anything dramatic. This was not an earthquake. Not an eruption, nothing sudden enough to notice in a single afternoon. It was something slower and stranger than that, an entire continent quietly beginning to come undone from the inside. If you want to watch something similar to this exact process happening on our own planet right now tonight, you barely need to leave the modern map. Down through eastern Africa, stretching from the Red Sea coast, down through countries like Ethiopia, Kenya and Tanzania, the ground itself is doing this same slow work today. Geologists call it the East African Rift, and it is quite literally a continent splitting itself apart in extraordinarily slow motion, roughly at the same speed your fingernails grow. In one particular corner of Ethiopia, a scorching, low-lying stretch of desert called the Afar Triangle, 3 separate rift systems already meet at a single point, a place geologists sometimes describe as the closest thing on dry land to a brand new ocean being born in real time. Scientists estimate that within some tens of millions of years, the eastern edge of Africa will eventually separate, entirely opening a brand new ocean basin where dry land currently sits. People go about entirely ordinary lives across that landscape today, farming, raising families, building cities, largely unaware that the ground beneath their homes is executing the opening act of the exact same slow-motion drama that once played out across an ancient supercontinent well over 1 billion years earlier. Now here is where tonight's story takes a turn I honestly did not expect when I first started researching this particular chapter, and it is the part of tonight's journey I am most excited to finally share with you. Before we get to that, though, it helps to understand how geologists even manage to date an event this old, this slow and this quiet. When a landmass starts stretching apart like this, molten rock frequently seeps upward through the newly forming cracks, cooling into long, straight wall, like formations called dikes, sometimes stretching for hundreds of miles in a single, nearly straight line across the landscape. Because these dikes only form when the crust above them is actively being pulled apart, and because the minerals inside them can be dated with real precision, a cluster of dikes all pointing in roughly the same direction, all cooling around roughly the same time, becomes something similar to a signed and dated receipt for exactly when and in which direction an ancient continent first started coming apart. Researchers have found several such clusters connected to this particular supercontinent, scattered across rock in Canada, Scandinavia, and elsewhere, all quietly agreeing on the same rough window of time. For a long time, most geologists studying this ancient supercontinent's breakup treated it as a fairly minor detail, a tectonic footnote sitting somewhere inside an already uneventful billion years. But a research team working out of the University of Sydney and the University of Adelaide recently built something remarkable, an entirely new detailed model tracking plate movement across this planet's surface, stretching back across the full 1.8 billion years we've spent tonight exploring together. Led by a researcher named Dietmar Müller, this team pieced together in far more detail than anyone had managed before exactly how the edges of every continent shifted, expanded, and reshaped themselves across this enormous stretch of time, cross-checking their reconstruction against exactly the kind of dike evidence and the kind of paleomagnetic evidence we talked about earlier tonight, along with a wide range of newer geochemical data nobody had access to even 10 years ago. What they found quietly rewrites a piece of the story I told you earlier tonight. When this ancient supercontinent finally began splitting apart in earnest, somewhere near 1.46 billion years ago, something happened to this planet's coastlines that nobody had fully appreciated before. Remember, a single joined landmass has comparatively little total coastline, since fewer separate continents simply means fewer separate edges touching the ocean. But when that landmass finally started cracking apart into multiple pieces drifting away from each other, the total length of shallow coastline scattered across this planet did not just increase. According to this new research, it more than doubled, stretching out to somewhere around 130,000 kilometers of brand new shallow sunlit continental shelf. Can you picture that kind of expansion for a moment? Not a modest improvement, not a small correction. More than double the shallow, nutrient-rich sunlit ocean edge available to any living thing trying to make a home there. Picture the difference between a single narrow hallway and an entire building's worth of open rooms suddenly available on the exact same afternoon. Those shallow coastal shelves matter enormously if you remember our earlier conversation about the reduced coastline this same supercontinent once caused simply by existing. Shallow water is where sunlight actually reaches the seafloor. It is where nutrients washing off the land actually settle instead of sinking uselessly into the deep ocean. It is in almost every meaningful sense the most valuable real estate an ocean has to offer anything trying to grow, reproduce, or diversify. And according to this newer research, this dramatic expansion in shallow coastline lines up almost precisely with a corresponding rise in oxygen, reaching those same waters, along with a documented uptick in the diversity of complex eukaryotic life, exactly the kind of organism we spent the last part of tonight's journey watching, quietly take shape inside a single ordinary cell. There's a fairly simple, almost intuitive chain of cause and effect sitting underneath all of this once you lay it out plainly. More coastline meant more places for early eukaryotic organisms to actually settle and take hold. More settled organisms meant more localized photosynthesis happening in shallow sunlit water. More localized photosynthesis meant more localized oxygen production, concentrated exactly where these young energy-hungry mitochondria-powered cells needed it most. None of this required anything dramatic or sudden. It simply required more room, and more room, it turns out, was exactly what this planet had been quietly denying itself for the entire length of time this ancient supercontinent stayed whole. I want to sit with the size of that correction for a second, because I think it deserves more than a passing mention. This is not a minor academic footnote. This is an entire research team looking directly at the so-called boring billion, the exact stretch of time scientists spent decades dismissing as an evolutionary dead zone, and discovering that one of its defining hidden turning points was not boring at all. It was a quiet planet-wide renovation project, expanding the available living space on this entire world by more than double right at the exact moment complex life needed room to start experimenting with what it could eventually become. Here is a question worth turning over while you picture that ancient coastline stretching out in every direction, further than it had in over 1 billion years. How many things in your own life have you privately written off as uneventful, only to discover much later that something enormous had actually been quietly reshaping itself underneath the whole time? I think about this particular correction a little differently than most of the facts we've covered tonight, if I am honest with you. It is not simply a fact about ancient Earth. It is a small, humbling reminder about how easily an entire field of very smart, very careful scientists can look directly at something for decades, decide they already understand it, and still eventually need to go back and completely rewrite the story once better tools finally arrive. Textbooks printed only a handful of years ago still describe this entire billion-year stretch, using language that this newer research is actively quietly correcting right now, while you listen to this tonight. If professional researchers can spend this long quietly, misjudging an entire chapter of planetary history, the rest of us can probably extend ourselves a little grace too, the next time we assume we already have someone or something fully figured out. There is something else worth sitting with here too, something a little more personal if you will let me linger on it for a moment. This particular supercontinent, the one we spent so much of tonight watching slowly, patiently come together, was now just as patiently coming apart. And rather than being some kind of failure, some kind of undoing of everything that had been built, this breaking apart turned out to be exactly what the rest of the story needed in order to continue. More coastline, more sunlight reaching more water, more room for life to finally stretch beyond what it had already mastered. Have you ever gone through an ending like that yourself? A relationship, a job, a version of your own life finally cracking apart after holding steady for a very long time, and only understood much later that the breaking itself was what made room for something larger to finally grow. I do not think every ending deserves to be treated as a tragedy simply because something that once felt permanent stopped holding together. Sometimes the exact thing that needs to come apart is the very thing that was quietly limiting how much room anything inside it had left to grow. This ancient landmass held itself together for the better part of 1 billion years, and that stillness mattered enormously. We spent a good portion of tonight's journey making that case. But its ending mattered just as much. Life on this planet did not need this particular supercontinent to stay whole forever. It needed it to stay whole exactly long enough, and then eventually to let go. I think that is the part people rarely tell you in the middle of an ending like that, while everything you built together is still visibly splitting apart. Nobody promises you in that particular moment that all this room being carved open around you will eventually fill with something worth having. You mostly just feel the cracking. The rest, the wider coastline, the better light, the unexpected room, to finally grow into something you could not have grown into before tends to become obvious only much later looking back. the same way it took this planet's own scientists well over 1 billion years to notice what this particular ending had actually made possible. Out along those newly widened coastlines in water, finally shallow enough, warm enough, and rich enough for something new to take hold, the descendants of that quiet cellular partnership we discussed a little earlier tonight were finally about to attempt something else this planet had never once seen before. Not simply surviving, not simply growing larger or more complex in isolation, something considerably stranger and in its own quiet way, considerably more intimate than anything we have covered so far tonight. It would not happen everywhere at once, and it would not happen quickly even by the patient standards this planet has already shown us tonight. But somewhere along one particular stretch of that newly opened coastline inside a shallow tide pool warmed by an ordinary afternoon sun, something was about to happen that had never once occurred in this planet's entire 4.5 billion year history. And once it did, absolutely nothing about the future of life on Earth would ever look quite the same again. Picture the tide pool first, because everything else tonight depends on you actually seeing it. Shallow, warm by the standards of this era, rimmed by pale, mineral-streaked rock, the kind of pool that fills at high tide and sits quietly cooking in the sun until the water finally returns for it. Somewhere beyond it, the wider coastline we left behind a little earlier tonight stretches out in every direction. Wider now, sunnier now, exactly the kind of newly opened shoreline this planet had been quietly denying itself for the better part of 1 billion years. Along one edge of this particular pool, clinging to the stone in thin reddish threads, barely visible unless you lean in and look carefully, something is growing that looks at first glance almost exactly like the algae you might absent-mindedly brush off a rock during any ordinary beach vacation today. And in one specific sense, that first impression would not be far wrong at all, because this particular organism, so far as anyone can tell from the fossil record, was about to become the oldest known ancestor of something every single sexually reproducing creature on this planet still depends on. Every animal, every flowering plant, every one of us listening to this tonight. Scientists gave this organism a name that sounds almost like poetry if you say it slowly enough. Bangiomorpha pubescens, a small thread like red alga, its threads sometimes stretching only a couple of millimeters long, barely visible without real magnification. And tucked inside those threads, preserved in stone for well over 1 billion years, researchers eventually found something that had never been documented anywhere else in the entire fossil record before it. 2 distinct kinds of reproductive cells built into the very same organism doing 2 entirely different jobs. Some of these cells simply clone themselves, producing identical copies, a straightforward, efficient strategy. This planet's simpler organisms had already been relying on for well over 2 billion years. By this point, the exact strategy we spent so much of tonight's journey admiring for its quiet, patient success. But other cells inside this same small alga were doing something different, something considerably more complicated. They were producing spores specifically built to combine genetic material from 2 separate parent lineages, rather than simply copying one. In other words, this humble little strand of red algae was doing both at once the old reliable trick and an entirely new one side by side inside a single organism smaller than your fingernail. I want to pause here because I think it helps to understand exactly why this distinction matters so much beyond simply being an interesting fact to fall asleep to. Cloning is fast, it is efficient, it requires no partner, no coordination, no risk of anything going wrong along the way. Plenty of organisms today still lean heavily on it. Certain starfish can regrow an entire new body from a single severed arm, and some houseplants people keep on a windowsill will happily grow an identical copy of themselves from nothing but a cutting placed in a glass of water It works. It has always worked. But it also produces offspring that are generation after generation essentially identical to the parent, carrying forward the exact same strengths and the exact same weaknesses indefinitely, like photocopying the same page over and over without ever once being allowed to edit it. Combining genetic material from two separate individuals is slower, riskier, and considerably more complicated to coordinate. But it does something cloning simply cannot. It shuffles the genetic deck completely fresh, with every single generation producing offspring that are subtly, meaningfully different from either parent, carrying new combinations of traits that natural selection has never had the chance to test before. Here is a question worth sitting with while you picture that shuffled deck. If cloning is faster, safer, and easier, why would evolution ever favour something slower, riskier, and considerably more complicated instead? It seems on the surface like an almost irrational trade to make, giving up a strategy that had already worked perfectly well for well over 2 billion years, in favour of something this much more complicated to coordinate. The honest answer took biologists a long time to work out properly, and there is still real active debate about the details. But the broad shape of it comes down to something like this. A world that never changes rewards perfect copies. A world that keeps shifting new diseases, new competitors, new chemistry in the water rewards variety instead. Since somewhere inside that freshly shuffled genetic deck, there is a better chance that at least one offspring happens to be carrying exactly the right combination of traits for whatever challenge shows up next, and by the time this particular alga was growing quietly in its tide pool, this planet, as we have spent this entire night discovering, had already been through fire ice poisoned oceans and a supercontinent slowly splitting itself apart. A world with that particular resume, it turns out, rewards a freshly shuffled deck rather generously. Before we go any further, there is a second quieter piece of biology tucked inside this same tiny organism, worth mentioning, one that connects directly back to something we spent time on earlier tonight. Remember that ancient partnership, one simple cell swallowing another and keeping it alive instead of digesting it? The story that eventually gave rise to the very structure now converting oxygen into energy inside your own cells. This little red alga carries evidence of a second separate partnership, just like it considerably later in this planet's story. An ancestor of this exact organism once swallowed a different kind of bacterium entirely, a photosynthetic one, and kept that one alive too. That surviving photosynthetic bacterium eventually became the chloroplast, the tiny internal structure responsible for capturing sunlight and turning it into food, the very reason this little alga carried any colour at all. Two separate accidental partnerships, roughly 700 or 800 million years apart, quietly stacked on top of each other, inside the same tangled family tree, each one on its own, reshaping what life on this planet could eventually become. It is a strange thing to sit with that the ordinary red tint clinging to that rock in front of you is itself a kind of fossil evidence of an ancient merger, still quietly working generation after generation inside a living cell. Now, how does anyone actually find something this small, this old and this fragile sitting inside solid rock? Credit for this particular discovery belongs largely to a researcher named Nicholas Butterfield, who first properly described these fossils in the early 1990s, pulled from remote windswept rock formations on Somerset Island deep in the Canadian Arctic. Getting there at all involves flying into some of the most isolated research stations on the entire planet, hauling equipment across terrain that stays near freezing for most of the year, all to chip carefully through layers of stone. Nobody else had ever thought to look at quite this carefully. For years afterward, though, one stubborn question kept nagging at researchers studying this particular fossil. Exactly how old was it? early estimates placed it somewhere near 1,200,000,000 years old, but the uncertainty attached to that number stretched embarrassingly wide enough that some skeptical researchers wondered whether the fossil might actually be several 100 million years younger than originally claimed, which would have made it a considerably less remarkable discovery. Enter a graduate student named Timothy Gibson working out of McGill University roughly 2 decades after the fossil's original discovery. Rather than trying to date the algae directly, which is notoriously difficult with organic material, this delicate Gibson's team instead collected samples of the dark mineral-rich shale surrounding the fossil-bearing rock layers and applied a precise dating technique built around 2 rare elements, rhenium and osmium, which decay from one into the other at an extremely steady, well-understood rate locked inside certain kinds of ancient mud. It is in its own way a little like carbon dating's older, sturdier cousin built for stretches of time so vast that ordinary carbon dating simply gives up and stops working. The result, published in a respected scientific journal in the year 2018, settled the question with far more precision than anyone had managed before. 1,047,000,000 years old, with an uncertainty of only about 15 million years in either direction, a remarkably tight window for something this ancient. I find something quietly satisfying about that particular resolution, if I am honest with you. An idea sitting slightly uncertain for decades finally nailed down not by finding a better fossil, but by getting patient, careful, and clever enough about the rock surrounding it instead. Now here is a correction worth making before we go any further, because I think the honest version of this story deserves it the same way it has deserved it every time tonight's journey has bumped into a headline that oversells itself. This particular fossil did not literally invent sexual reproduction the way a single clever engineer might invent a new tool. Simpler versions of genetic recombination likely existed earlier, tucked inside organisms too small, too soft, or too poorly preserved to ever leave a fossil trail we could find. Some researchers suspect the underlying machinery for combining genetic material may stretch back considerably further than this fossil, hidden inside ancestors we may never manage to identify with any real confidence. What makes this particular alga so remarkable is not that it was first in some absolute sense nobody can actually prove. It is that this is the oldest place in the entire fossil record where we can physically see the evidence sitting right there in the stone, 2 different deliberately built reproductive strategies captured together inside one clearly identifiable ancestor of a group still alive on this planet today. I keep thinking about the actual biological cost of what this little organism was doing, and how strange it is that evolution favoured it so decisively in the end. Combining genetic material with another individual means giving up half of what you would otherwise pass along entirely on your own. It means depending on something outside yourself, something you cannot fully control, in order to create the next generation. Cloning never asks for that particular kind of vulnerability. It simply repeats what already worked. Have you ever noticed how the safest, most self-contained choice in your own life is rarely the one that actually helps you grow the most? There is nothing almost tender about it if you let yourself sit with it for a moment. This tiny ancient organism growing quietly in a shallow, forgettable tide pool essentially decided that combining itself with something outside its own boundaries was worth the risk, worth the loss of perfect self-sufficiency, because whatever came out the other side would be able to meet a changing world more capably than either parent could have managed completely alone. It is in its own quiet cellular way one of the oldest arguments this planet has ever produced for choosing connection over easy, comfortable isolation. I think about that particular trait every time I hear someone describe love or friendship or even simple collaboration as somehow less efficient than going it alone. In a narrow short-term sense, that is often true. Solitude asks nothing of you. It cannot disappoint you, cannot complicate your plans, cannot force you to compromise on anything at all. But 1 billion years of evidence quietly sitting inside a strand of red algae smaller than your fingernail suggests that efficiency was never really the point. Resilience was. And resilience, more often than any of us would like to admit, seems to require letting something outside yourself in. Out from that one small thread like alga, an entirely new category of relationship had entered the story of life on this planet. One that would eventually make possible every family, every partnership, every act of combining two separate lives into something neither one could have built completely alone. But this particular alga, remarkable as it was still only clinging to a narrow strip of shoreline, still surrounded by a landmass that had already spent so much of tonight's story assembling and breaking and drifting apart. And somewhere out beyond that shoreline, the pieces of this restless world were already beginning once again to slowly drift back toward each other. The same patient forces that once gathered this planet's continents into a single, joined landmass, then patiently pulled them apart again, were quietly gathering themselves for a third attempt, a new assembly on a scale even larger than the one we already spent so much of tonight watching come together. This next assembly would carry a different name, and it would shape the world this small, alga's descendants were about to inherit in ways none of them could have possibly predicted. This next assembly carried a different name, one considerably softer than the last, and I happen to think the story behind that name deserves a moment of its own before we go anywhere else tonight. Back in 1990, a pair of researchers, a married couple named Mark and Deanna McMenamin, sat down to name this newly reconstructed ancient landmass, and instead of reaching for another geographic reference, the way earlier researchers had, they pulled from an entirely different well. They chose a Russian word Rodina, which roughly translates to motherland or homeland. Not Nuna's cautious scientific committee of names, not Columbia's quiet turf war between two research teams. Just one single, almost tender choice, a name meant to capture the sense that every piece of land currently scattered across this planet, every mountain range you have ever stood on, ultimately traces its roots back to this one ancient unified home. I like to imagine that particular naming conversation happening somewhere quiet, maybe over dinner, two people who study deep time for a living, deciding that this particular chapter of Earth's story deserved a word with a little warmth in it, rather than another string of careful, defensible geographic references. This time, though, the process of coming together looked considerably different than it had the first time around. Remember how gently this planet's first supercontinent assembled all those hours ago in tonight's story landmasses, drifting together slowly, almost politely, like two crowds merging at the edges of a gathering. Rodinia's assembly was not nearly so gentle. Somewhere between roughly 1.3 billion and 900 million years ago, the fragments left behind by that earlier supercontinent's breakup began colliding again, but this time with considerably more force, crumpling and thickening the crust wherever they met, throwing up mountain ranges that would have rivaled or possibly even surpassed the height of the modern Himalayas. Where the first assembly had been a quiet convergence, this one played out more like several enormous ships still moving at a speed too slow for any single eye to catch, but colliding with enough accumulated force to buckle solid stone upward by miles, folding entire layers of rock back over themselves the way a rug bunches up against a doorframe. And by most reconstructions, this second supercontinent ended up more complete than the first one ever managed, drawing in nearly every scrap of continental crust this planet had to offer, rather than leaving stray pieces scattered along the edges the way its predecessor had. Geologists call this particular chapter of mountain building the Grenville orogeny, and unlike almost everything else we have discussed tonight, this one left behind evidence you can still walk across today, without needing a laboratory or a research vessel to find it. Here is where I want you to actually picture something real, something you may have driven past, hiked across, or seen in a photograph without ever knowing what you were looking at. The worn rounded peaks of the Adirondack Mountains in upstate New York, popular today with hikers who mostly have no idea they are walking across the root of a mountain range that once stood taller than anything currently on Earth. Deep sections of the Blue Ridge Mountains running down through Virginia and North Carolina, the same soft blue tinted ridgeline countless families have photographed from countless overlooks, without ever suspecting its deepest bedrock formed during a collision over 1 billion years old. This same belt of ancient deformed rock keeps stretching quietly beneath the surface from the coast of Labrador in the far north, all the way down through Texas and into Mexico in the south, an underground scar running the length of an entire continent, rock formations stretching as far as the Scottish Highlands on the completely opposite side of the modern Atlantic Ocean, since this same mountain-building event, remember, happened before that ocean even existed to separate these two landscapes at all. All of it, every single one of these places contains ancient bedrock forged during this exact same mountain-building event over 1 billion years ago, when all of these locations sat crushed together inside the same violent collision zone. The mountains themselves have eroded down to a fraction of their original height, worn smooth by well over 1 billion years of nothing but rain and time, but the deep twisted heat and pressure-altered rock underneath them is still sitting there right now, quietly holding the memory of a collision. Most people driving past it have never once considered, have you ever stood somewhere ordinary, a hiking trail, a scenic overlook, a familiar drive you've taken 100 times, and later found out something remarkable had happened there long before you ever showed up? I think about that possibility now, every time I see a mountain range on a road trip, wondering exactly how much violent ancient history is quietly folded into whatever unremarkable hillside happens to be passing by the window. I think there is something worth noticing in the contrast between how gently this planet's first supercontinent came together and how violently its second one did. It is tempting to assume that meaningful change should always look the same, quiet and gradual, the way we spent so much of tonight's earlier journey admiring patience and stillness. But this particular chapter argues against that assumption rather forcefully. Sometimes the version of coming together that actually matters looks less like two crowds gently merging, and more like an entire mountain range violently thrown skyward in the process. Neither one is wrong. They are simply different shapes that the exact same underlying need continents finding their way back to each other happen to take. Now, exactly what did this newly assembled landmass actually look like? Here, honestly, I have to give you the same caveat I have given you before tonight, because the honest answer involves real ongoing disagreement among the researchers who study it. Most reconstructions place ancient Laurentia, the same core of rock that once sat near the heart of this planet's very first supercontinent, once again somewhere near the center of this second one, an odd kind of geological déjà vu, the same familiar piece of ground finding its way back toward the middle of the map, twice across a gap of hundreds of millions of years. It is worth pausing on that particular detail for a moment, honestly. Twice this exact same patch of ancient stone. The deep rock now sitting beneath so much of modern Canada and the northern United States found its way back to roughly the same position at the center of an entirely new arrangement of continents, as though certain pieces of this planet simply keep finding their way back to the middle of the story, no matter how many times everything around them gets rearranged. Beyond that shared core, though, the exact arrangement of everything else remains actively contested. One particularly debated proposal, sometimes nicknamed the sweat hypothesis, suggests that a stretch of what is now the southwestern United States once sat pressed directly against a stretch of what is now East Antarctica. Two regions separated today by an entire hemisphere, once near enough, according to this particular model, to share a single mountain range. Other researchers argue the fit does not work nearly as cleanly as its supporters claim. The debate remains active in scientific journals published within the last few years, which tells you something important about how stubbornly much of deep time still resists a tidy, settled answer. There is a quieter consequence to all this mountain building worth mentioning too, one that connects directly to a much bigger story we've not fully told yet tonight. Freshly thrown up mountain ranges, still jagged, still exposed weather considerably faster than the old, worn-down terrain ever does. Rain falling across raw, newly exposed rock triggers chemical reactions that slowly pull carbon dioxide directly out of the atmosphere, locking it away inside solid minerals instead. A little of this weathering happens everywhere all the time, quietly balancing this planet's climate over long stretches of time. But a sudden planet-spanning burst of fresh, jagged mountain range thrown up all at once across multiple continents pulls considerably more carbon dioxide out of the sky than this planet's climate had been used to managing. I will not pretend that story finishes tonight, because it honestly does not, but it is worth sitting with the seed of it for a moment. A planet that had just spent so much of tonight's story finally settling into balance was quietly setting up a fairly serious climate experiment for itself without meaning to one mountain range at a time. I keep thinking about the shape of this particular return, if you will let me linger on it a little longer. This was not simply the old supercontinent reforming itself back into an identical copy of what it used to be. Some of the same pieces came home Laurentia chief among them, but they arrived alongside new partners in new configurations, forced together by new considerably more violent collisions than the ones that first brought them together the last time around. Have you ever gone back to something familiar after a long time apart, a place or relationship, even a version of yourself you thought you had left behind, and found that it was not quite a return to what it used to be, so much as a new arrangement built out of familiar pieces? I do not think that is a small thing to notice, honestly. We tend to imagine healing or rebuilding or reconciliation as a return trip, as though the goal is always to get back to exactly where things stood before everything came apart. This particular mountain range suggests something a little more honest than that. The old core came home, but everything built around it was new, forged under new pressure, shaped by everything that had happened in between. Maybe that is closer to how most meaningful returns actually work, less like reversing time and more like building something that only makes sense once you already understand everything that had to fall apart first. You do not get the old version back. You get something sturdier, occasionally taller than anything that existed before, built directly on top of the exact ground that once broke. Out across this newly thrown up, violently assembled landmass, life continued on, largely as it had before, small, patient, and mostly unaware of the mountains rising somewhere off in the distance. But something about the sheer scale of everything we have covered across tonight's entire journey deserves a moment of its own before we keep moving forward. Think about everything this single, supposedly boring billion years actually contained. A poisoning that reshaped the entire atmosphere and nearly wiped out most of the life witnessing it. An ice age long enough to make recorded human history look like a single afternoon. An ocean quietly layered with toxic sulfur-rich water and tucked inside the same water communities of bacteria, turning that poison into a strange, glowing kind of beauty. Countless generations of small patient organisms quietly perfecting the exact same design for a billion years straight, never once mistaking stillness for failure. a silent partnership between two separate cells that eventually made every complex form of life on this planet possible, defended for decades by a young scientist nobody believed at first. A second partnership considerably later that gave a small red alga its color, an entire continent gathering itself together, holding steady for the better part of 1 billion years, breaking apart again once that stillness had done its work, and then gathering itself into something even larger the second time around. And somewhere inside all of that noise disguised as silence, an organism figured out how to combine itself with something outside its own boundaries and decided that risk was worth taking. If you step back far enough from any single chapter of tonight's story and look instead at the whole shape of it, laid out together, a rather different kind of picture starts to come into focus, one this planet's own scientists took a remarkably long time to notice clearly, and one I think deserves its own quiet, undivided attention before tonight's journey goes any further. Here is the different picture, the one I promised you a moment ago. Not long after everything we have spent tonight walking through in the grand scheme of this planet's timeline anyway, something considerably louder finally arrived. Roughly 540 million years ago, give or take, the fossil record suddenly, almost violently, fills up with an entirely new cast of characters. Creatures with eyes, some of the very first eyes this planet had ever produced, capable of actually seeing a predator coming rather than simply drifting blindly through the water. Creatures with legs, shells, claws, jointed limbs built for grabbing and hunting, an entirely new grammar of bodies showing up almost all at once after well over 1 billion years of this planet, mostly speaking in the same simple biological sentence over and over. Somewhere between 20 and 35 entirely new major branches of the animal family tree. The same broad categories every animal alive today still belongs to all, showing up more or less at once, inside a stretch of time lasting only around 20 million years. Geologists gave this particular chapter a suitably dramatic name, the Cambrian Explosion. It earned that name honestly. Compared to almost everything we have covered tonight, this truly was fast, dramatic and strange enough that even Charles Darwin, whose own sketch of a branching tree of life we talked about earlier tonight, considered it a serious problem for his entire theory. He called it in his own private notes something near a puzzle he could not fully solve, precisely because life seemed to go from almost nothing to almost everything, with barely any obvious warning beforehand. Here is what I want you to notice though, because I think it matters more than the explosion itself. Ask nearly anyone with even a passing interest in prehistoric life what they know about deep time, and they can usually tell you something about the Cambrian explosion. Museums build entire wings around it, full of trilobites and strange armoured creatures under dramatic lighting. Documentaries open with it, complete with sweeping music and slow-motion footage of imagined ancient seas. It has its own nickname, its own dramatic reputation, its own permanent place in the popular imagination, right alongside dinosaurs and asteroid impacts. Ask that same person what they know about the billion years sitting directly before it, the exact billion years we've spent this entire night walking through together, and you will typically get silence, or at best a vague memory of hearing it called boring, usually followed by an apologetic shrug as if there is nothing more to say about it. Can you see the shape of that particular unfairness now laid out plainly like this? Think back, if you can, to the very beginning of tonight's story all those hours ago when I first told you that the quietest chapter this planet ever lived through might be hiding its biggest secret. This is that secret laid out in full now. Not a single hidden event, not one dramatic reveal, but this entire pattern repeated over and over across tonight's journey, quiet stretch after quiet stretch, each one eventually proven to be doing far more work than anybody watching from a distance ever gave it credit for. The truth, as we have spent tonight patiently uncovering piece by piece, is that almost nothing about that Cambrian explosion could have happened without the billion quiet years sitting directly underneath it. The oxygen finally reaching a level complex animals could actually use. The partnership between two ancient cells that made large energy-hungry bodies possible in the first place. The invention of combining genetic material between two individuals quietly shuffling the deck for hundreds of millions of years before anything used that shuffled deck to build a shell or an eye. Even the mountains, the ones we spent time with only a little earlier tonight, likely played their own quiet part, since many researchers studying this transition suspect that Rodinia's breakup and all that fresh, eroding mountain rock washing new nutrients into the ocean helped set the stage for exactly the explosion that followed it. The quiet stretch was never separate from the explosion. It was the explosion's entire foundation, poured slowly, patiently, one unremarkable century at a time. I think there is something worth naming honestly here, something that goes beyond simple geology. We are all of us wired to notice sudden change and overlook gradual change almost completely. Psychologists actually have a name for a version of this tendency, something near what researchers call change blindness. Our brain's well-documented habit of failing to register a shift that happens slowly enough, even a fairly large one, while snapping instantly to attention, the moment something changes all at once. News coverage runs almost entirely on this same principle. A war breaking out gets covered obsessively. A slow decades-long improvement in something like global literacy or infant mortality barely gets mentioned at all, even though added up it may have changed more lives than the war did. Our attention quite simply was never built to notice the quiet, compounding kind of progress. It was built to notice the loud kind. Even professional scientists trained specifically to notice patterns other people miss fell for this exact same trap for decades, dismissing an entire billion years of Earth's history with a nickname that stuck a little too well. If people who spend their entire careers studying deep time can still walk straight past this particular blind spot, the rest of us probably deserve a little more patience with ourselves the next time we mistake our own quiet seasons for wasted ones. You can watch this same blind spot play out in far smaller, far more ordinary corners of life too. Ask anyone who has patiently set aside a small amount of money every single month for 20 or 30 years quietly, without any fanfare, and they will usually tell you the same thing. For most of that stretch, absolutely nothing seemed to be happening. The account barely moved month over month in any way that felt worth mentioning to anyone. And then seemingly out of nowhere, usually somewhere near the end of that stretch, the growth suddenly becomes dramatic, almost explosive, purely because of how compounding quietly works, stacking small invisible gains on top of each other for years, before the shape of the whole thing finally becomes visible all at once. Nothing sudden actually happened in that final dramatic seeming stretch. The quiet decades simply finished doing the work they had been doing patiently the entire time. Because I do not think this particular blind spot stays confined to geology, or news coverage, or old bank statements. I think most of us are carrying around a version of it in how we judge our own lives. Think about the stories we actually tell each other, the ones that make it into a toast at a wedding, a caption under a photo, a proud message to a parent, the promotion, the wedding itself, the diagnosis that finally resolved, the finish line crossed. Every one of those moments is real, and every one of them deserves to be celebrated exactly the way it usually is. But almost none of those moments explain themselves. They all sit on top of something considerably quieter, considerably longer, and considerably less photogenic underneath them. Years of unglamorous effort nobody filmed. Countless ordinary Tuesdays that never made it into any story anyone told afterward. A relationship slowly and visibly repairing itself across 100 small, unremarkable conversations nobody thought to write down. Think about anyone you have ever watched become truly skilled at something, playing an instrument, speaking a second language, fluently running a small business that finally started supporting a family. Nobody ever asks to see the first 18 months of that particular story, the clumsy scales, the embarrassing mistakes, the quiet months where the business barely broke even, and it would have been so easy to quietly give up without anyone even noticing. We only really show up for the recital, the fluent conversation, the grand opening. The quiet, unglamorous middle almost never makes it into the story at all, even though it was doing considerably more of the actual work than the final photographed moment ever did. Have you ever looked back at some truly significant turning point in your own life and realized only in hindsight just how much quiet, unglamorous groundwork had actually been sitting underneath it the whole time, completely unnoticed while it was happening? I think about parents a great deal when I sit with this particular idea, if I am honest with you. Nobody builds a museum wing around the 11,000th ordinary breakfast made before school, the quiet repeated reassurance offered at 2 a.m, during a difficult year, the small patient consistency that never once asks to be noticed, let alone celebrated. Ask most adults what actually made them feel safe growing up, and they rarely point to one single dramatic moment. They point to a pattern, 1,000 small repetitions of someone simply showing up again and again in exactly the same reliable way. And yet, if you trace nearly any adult's steadiest, most secure qualities back far enough, you will almost always find some version of that exact quiet consistency sitting underneath it, doing work every bit as important as anything that eventually got its own photograph. I think about recovery the same way too, whatever form it happens to take in someone's particular life. The dramatic before and after photograph gets shared. The actual work, the hundreds of unremarkable days spent simply choosing again to keep going, almost never does, because there is nothing especially photogenic about an ordinary Tuesday spent staying the course. But those ordinary Tuesdays stacked up patiently one after another are not separate from the eventual breakthrough. They are the exact same relationship this planet's billion quiet years had with the explosion of life that eventually followed them. The quiet part was never the empty part. It was simply the part nobody thought to put a name on, until eventually someone did and got the name wrong. If tonight's story has a single thesis sitting underneath everything else we've covered, I think this might be it. We keep telling history and telling our own lives as a sequence of loud, dramatic turning points, stitched together by boring connective tissue we mostly skip past. But the quiet stretches were never simply connective tissue. They were where almost all of the actual work happened. The turning points are just where that work finally became visible enough for someone to notice and give a name and build a museum wing around. 1 billion years of this planet's history got dismissed with a single careless nickname right up until a handful of patient researchers finally looked closely enough to notice otherwise. I wonder honestly how many quiet stretches of our own lives are still waiting on that same kind of second look, still sitting there patiently doing important work nobody has bothered to properly notice yet. I do not say any of this to diminish the loud moments, the explosions, the finish lines, the milestones worth celebrating exactly as loudly as we already do. I say it because I think the quiet moments deserve at least a fraction of that same respect, even though they will probably never get their own dramatic name, their own museum wing, their own place in a toast at somebody's wedding. If you are inside a quiet stretch of your own life right now, still waiting for something worth photographing to happen, I hope some part of tonight's story has managed to sit with you a little differently than it might have 4 or 5 hours ago. Because this particular planet's story was not finished settling into calm, not entirely. Even as that first explosion of complicated life was still gathering itself somewhere off in the distant future, the quiet, patient world we've spent all night getting to know was already slowly beginning to show its very first cracks. Small at first, easy to miss, the kind of change that would have looked to anyone standing on that ground at the time like absolutely nothing worth mentioning at all. You would not have noticed it if you had been standing there, somewhere along the northern edge of this vast joined landmass, roughly in the stretch of ground that will one day become Alaska, northern Canada, and the coast of Greenland, the ground itself, had started almost imperceptibly to swell. Nothing dramatic, no sudden tremor, no obvious warning. Just the faintest, slowest kind of lift, the same kind of quiet stretching we watched happen once already tonight, deep beneath an earlier supercontinent's heart, except this time playing out along Rodinea's northern edge, instead somewhere near 800 million years ago. If you had walked that particular stretch of coastline on an ordinary afternoon, you would have felt nothing under your feet worth mentioning, no hint at all that the ground itself had quietly begun keeping a different kind of schedule than the one it had followed for the last several 100 million years. Underneath that swelling ground, something enormous was gathering itself. What eventually broke through was not a single volcano the way most of us tend to picture volcanic activity. One cone, one column of smoke, one dramatic eruption you could point a camera toward and capture in a single frame. It was something considerably larger and considerably stranger than that. Molten rock began forcing its way upward across an almost unimaginable stretch of northern Laurentia, not through one narrow opening, but through countless fissures, sills, and shallow chambers spread across an area geologists now estimate at somewhere over 2 million square kilometers, a stretch of erupting, hardening basalt larger than the entire country of Mexico. Researchers call this the Franklin Large Igneous Province, and it stands today as one of the single largest volcanic events in this planet's entire 4.5 billion year history, dwarfing almost anything that has erupted on Earth since. Picture that scale for a moment if you can, without letting it feel too overwhelming to hold on to right before sleep. An area larger than most modern countries quietly filling with fresh, dark, cooling rock, not all at once, but across a span of a few million years, layer stacking on layer, sill after sill, an entire corner of this ancient supercontinent slowly turning into something closer to a permanent volcanic wound. If you flew over that stretch of ancient Laurentia during this particular chapter, you would have seen something closer to a slow, dark bruise spreading across the northern edge of the map, rather than any single dramatic mountain of fire most of us instinctively picture when we hear the word volcano. Here is the part of the story that took researchers considerably longer to piece together, and it is the part I find most quietly remarkable out of everything we have covered tonight. Fresh basalt, the exact kind of rock pouring out across this enormous stretch of northern Laurentia, weathers considerably faster than most other kinds of rock, especially in warm, wet conditions, since its minerals are simply less stable, less settled, more eager to react with rainwater than older, harder stone ever is. And Rodinia, during this particular stretch of its long existence, happened to sit largely clustered around the planet's tropical belt, drenched in exactly the kind of heavy warm rainfall that breaks fresh volcanic rock down fastest. Picture an entire country-sized stretch of brand new, still cooling stone sitting directly underneath a tropical downpour, century after century each storm quietly working a little more of that fresh rock apart at the molecular level. Rain falling across all that freshly exposed basalt triggered chemical reactions considerably more aggressive than the ordinary background weathering we talked about a little earlier tonight, pulling carbon dioxide out of the atmosphere at a pace this planet had rarely, if ever, experienced before. Have you ever watched a single, seemingly isolated event quietly set off a chain of consequences so much larger than anyone involved could have possibly anticipated at the time? A geologist named Francis MacDonald, working with a team of researchers across several institutions, spent years trying to pin down exactly how these two events, the eruption and whatever climate catastrophe followed, it actually lined up in time. This was not the kind of question you could answer by simply squinting at two rock layers and guessing which one sat on top of the other. Precisely dating volcanic rock this old, and precisely dating the very first evidence of the ice age that followed it, required extracting tiny mineral grains called zircons from both grains smaller than a grain of sand, and measuring the slow, steady decay of uranium locked inside them, one of the most exact clocks available to modern geology. Samples had to be collected from remote, difficult-to-reach outcrops scattered across the Canadian Arctic, transported back to laboratories, and processed with a level of patience that mirrors in its own small way the very patience this entire night's story has been asking you to sit inside. When the results from both finally came in, published in a respected scientific journal, the two events lined up almost exactly. The eruption. Then within a remarkably narrow window afterward, the ice. I want to sit with the precision of that particular finding for a moment because I think it deserves more weight than a simple fact usually gets. This was not two separate events that happened to occur somewhere in the same rough era of deep time, decades or centuries apart, near enough to seem loosely connected if you squint. The dating came back tight enough, a difference measured in a few 100,000 years at most, against a backdrop of well over 1 billion years, that most researchers studying it now consider the connection considerably more than coincidence. An entire corner of this ancient supercontinent quietly, almost accidentally engineered the beginning of its own undoing, one drop of rain hitting one stretch of fresh volcanic rock at a time. What followed, researchers now believe, was the first truly global ice age this planet had experienced in well over 1 billion years, the first one since that long ago stretch of fire and frost we spent time with near the very beginning of tonight's journey. There is something almost symmetrical about that particular detail if you sit with it for a moment. The exact 1 billion years we have spent all night walking through began with an ice age, and now, quietly at the far edge of that same stretch, another one was gathering itself to complete the loop. Evidence for this particular ice age, sometimes called the Sturtian glaciation, now turns up on nearly every continent on Earth, tucked into layers of ancient ice-scarred rock. Some of it, according to careful paleomagnetic study, laid down astonishingly near the equator itself, suggesting ice may have reached far nearer to the middle of this planet than anything in human experience could ever prepare you to imagine. I'm not going to walk you the rest of the way into that particular chapter tonight. Some stories deserve their own quiet room to breathe in, rather than being folded hastily onto the end of a night that has already carried you across an entire 1 billion years. But I did promise you, right at the very beginning of tonight's journey, that the quiet chapter we've spent all night inside was bordered on both ends by something considerably more dramatic. We spent real time earlier tonight with the first of those two borders, the fire and the poison, and the frost that came before this long calm ever settled in. This is where that second border finally starts coming into view quietly, at the edge of a warm, unremarkable coastline, exactly the way the first one probably did too long before anyone was ever there to notice it happening. There is something a little different about sitting inside this particular moment of the story, if I am honest with you. Something distinct from everything else we have felt together tonight. Every previous turning point we walked through had the comfort of hindsight built into it. We already knew the whole time that the oxygen catastrophe eventually led somewhere survivable. We already knew the poisoned ocean eventually cleared. We already knew the broken supercontinent eventually gathered itself back together into something larger. But standing here at this exact quiet crack, forming along an ancient coastline, none of that comfort exists yet. Nobody living through this moment, if anything alive at the time could be said to live through anything at all, had the slightest idea whether what came next would be survivable. Have you ever stood at the edge of a change like that yourself, watching the first quiet cracks appear in something that had felt permanent with absolutely no way of knowing yet whether what came after would turn out to be a disaster, or simply the next chapter you had not been able to imagine your way into? I think that particular kind of uncertainty, standing at the edge of change without the comfort of already knowing how the story ends, might be one of the hardest feelings a person can sit inside. We spend so much of tonight's story getting to look backward, already knowing which quiet stretches turned out fine. Real life rarely offers you that same courtesy while you're actually living through the crack itself. You mostly just feel the ground shifting without a single guarantee about what waits on the other side of it. Maybe that uncertainty is exactly why we tell stories like this one in the first place, not because they hand us guarantees about our own unfinished chapters, but because they quietly prove that uncertainty has never once been a reason for a story to stop being worth telling. And yet, if there is one thing tonight's entire journey has quietly, patiently argued across fire and ice and poison and partnership, and mountains thrown up out of nothing, it might be this. This particular planet has never once needed certainty in order to keep going. It simply kept going one uncertain, unguaranteed century at a time, and let whatever came next arrive on its own schedule without ever once needing permission first. Somewhere out past that swelling northern coastline, past the first fresh basalt cooling under a warm tropical rain, the quiet billion years we've spent this entire night walking through was finally, unmistakably coming to its end. Not with the same kind of gentle settling we watched happen at the very start of tonight's journey, but with something considerably colder, waiting somewhere just past the edge of what we have covered together tonight. I keep thinking about how ordinary that particular stretch of coastline must have looked right up until it was not ordinary anymore. No dramatic music swelled underneath it. No single obvious sign separated the last ordinary afternoon from the first afternoon of everything that followed. That is, I think, how most real endings actually arrive, not as a single dramatic scene you could point to afterward, but as one more quiet, unremarkable day that simply happened to be sitting closer to the edge than anyone standing inside it could have possibly known. For now, though, I want to bring you back one last time to the place where all of this began, because I think tonight's story deserves to end exactly where it started, standing, quietly at the edge of that same ancient patient water, before any of this, the fire, the ice, the partnership, the shuffled genetic deck, the mountains, the cracks had even happened yet at all. Let's go back there now, gently, the way you might return to a room you only visited once, a long time ago, but never quite forgot. That same shallow shoreline, that same patient water lapping quietly against dark ancient stone, the same soft light, the same enormous oversized moon somewhere overhead, the same unhurried quiet we started this entire journey inside all those hours ago. Only now, instead of walking into it for the first time, you get to walk back into it already knowing everything it was quietly holding underneath its surface the whole time. Do you remember what I told you about this water all those hours ago, right at the very start of tonight's journey? I told you it shimmered with strange colours we would get to a little later. I think it is time, finally, to actually look at every one of them laid out together the way you might finally look back at old photographs from a single, impossibly long year of your own life. The very first colour this water ever wore for us tonight was rust. deep, quiet red settling slowly onto the ancient seafloor as newly made oxygen reacted with iron dissolved through the water layer after layer. Century after century, the exact same rust-coloured stone now sitting inside the steel of a car, a bridge, maybe the very bed frame underneath you right now. That colour came from catastrophe, an atmosphere transforming so completely it nearly ended almost everything alive to witness it. A poisoning that somehow eventually turned into the very air both of us are breathing tonight. Then further down, hidden from ordinary daylight, this same water eventually wore a colour almost nobody expects an ocean to hold. A strange shifting mix of green and violet communities of sulphur-breathing organisms, quietly turning poison into something you could only call beautiful if you happen to be the kind of creature capable of noticing beauty at all. That colour came from a world that never made it into any tidy textbook explanation, one honest correction at a time, patchy, uneven, considerably stranger than any single clean story could properly capture a whole hidden layer of this planet, living a completely different life than the one unfolding along the sunlit surface above it. And later still, this same water carried the faintest, quietest tint of red once more, this time from something entirely different than rusted iron. A small thread like alga, smaller than your fingernail, carrying inside itself a second borrowed partnership, a captured photosynthetic bacterium doing the quiet work of turning sunlight into colour and food at once. That particular red came from an organism willing to combine itself with something outside its own boundaries, the very first hint of an entirely new kind of relationship this planet had never once produced before, one that would eventually make every single family tree, including your own, possible at all. Rust, then green and violet, then a small deliberate red, each colour arriving quietly, each one eventually forgotten by almost everyone, except the handful of patient researchers willing to go looking for it buried inside rock most of us will never once see with our own eyes. Here is something worth sitting with for just a moment before we go any further tonight. Every single one of those colours was at the time it existed considered utterly unremarkable. Nobody watching that shoreline, if anything capable of watching existed at all, would have known they were witnessing anything worth remembering. And yet here we are, an entire billion years later, and I have just spent most of tonight quietly convincing you that each one of those forgettable colours changed absolutely everything that came after it. Do you think somewhere in your own life there is a colour like that too? A stretch of time you barely noticed while you were living inside it, that later turned out to matter considerably more than you ever gave it credit for at the time. Maybe it was a job you almost quit, an ordinary friendship. You nearly let drift a habit so small you would have laughed if someone told you it mattered. Most of us are probably carrying a colour like that somewhere quietly settling into place, long before we ever think to look closely enough to notice it. There is one more thread I promised to tie off properly before tonight's journey finishes, and it has been sitting quietly in the background this entire time, if you were paying careful enough attention to notice it. Remember the moon hanging closer in that ancient sky than the one you can see tonight, and the days themselves shorter, spinning past at a pace this planet has been patiently, gradually slowing down from ever since. Somewhere across this same billion years, that moon kept drifting almost imperceptibly farther away, and those days kept stretching almost imperceptibly longer. The same quiet, patient rhythm running underneath every single colour this water ever wore. Even time itself, it turns out, was never standing perfectly still tonight. It was simply moving too slowly for anyone standing on that ancient shoreline to ever notice it changing at all. I think that particular detail might be my favourite quiet thread in this entire story, if I'm honest with you. This planet was never actually motionless during any of the hours we've spent together tonight. Not once. The moon was moving. The days were stretching. The colour of the water kept shifting beneath a surface that looked from any single afternoon like absolutely nothing was happening at all. Stillness, it turns out, was always something of an illusion, a trick of how short our own attention happens to be measured against how patiently this particular planet actually moves. We call an entire billion years boring simply because we were never built to sit inside a single moment long enough to feel it changing the same way you cannot feel the second hand on a clock actually moving. Even though given enough time, it will eventually carry you somewhere completely different than where it started. And now, at the very edge of everything we have covered tonight, one final colour is quietly beginning to arrive. Somewhere out past that ancient shoreline in water that has already worn rust and green and violet and a small deliberate red, the first pale hint of something considerably colder is starting to creep in along the coldest edges of this world, the very first whisper of the ice that would eventually reach so much further than anyone standing there could have possibly imagined. White or something near it was about to become this water's final colour for a very long while, quietly settling over every other shade this ocean had spent 1 billion patient years learning how to wear. I am not going to walk you into that particular colour tonight. It deserves its own quiet evening, its own slow, careful unfolding, rather than being rushed onto the end of a story that has already carried you across an entire billion years of deep time. Before we let this particular night settle, though, I want to leave you with something a little more personal than a fact, if you will allow me that. Everything we spent tonight walking through, every colour, every partnership, every quiet century of patient repetition, is not actually gone. It never really left. It is sitting inside you right now, tucked into the deepest architecture of your own body, whether you were expecting a bedtime story to end quite this way or not. The small borrowed structure converting oxygen into energy inside nearly every one of your own cells tonight is a direct, unbroken descendant of that same accidental partnership we spent time with earlier. The particular way your own body came into existence, 2 separate lines of genetic material, quietly combining into something new, traces its lineage back through an unbroken chain to that same small ancient alga, deciding that connection was worth the risk. Even the ground underneath, wherever you happen to be lying right now, may quite literally be built from stone that once sat at the heart of an ancient joined supercontinent patiently, silently anchoring an entire world into calm. Every breath you have taken tonight without once thinking about it carries oxygen that traces its origin back to that same catastrophic world-altering event we spent time with near the very beginning of this journey. You're not simply someone listening to an old story about a distant planet tonight. You are the story's continuation, whether you ever intended to be or not. Have you ever stopped to consider just how much quiet ancient patience it actually took to arrive at this exact ordinary moment you hear listening to my voice, wrapped in whatever blanket you happen to be wrapped in right now? 1 billion years of oxygen slowly building. 1 billion years of a genetic deck being patiently shuffled generation after generation. 1 billion years of continents finding each other, losing each other, and finding each other again just to arrange the particular stretch of ground you happen to call home tonight. None of it was rushed. None of it could have been. If there is one thing I hope you carry out of tonight's story and into whatever sleep is waiting for you now, it might be this. Whatever quiet, uneventful stretch you happen to be living through in your own life right now, whatever season feels a little too ordinary to mention to anyone, a little too slow to photograph, a little too repetitive to celebrate, it is doing far more work than it is currently getting credit for. This entire planet is living proof of that particular pattern, over and over for 4.5 billion years running. Quiet was never the opposite of important. It was simply patient about proving it. I do not know what particular season you happen to be sitting inside tonight, whether it feels closer to the calm of the very first shoreline we visited, or closer to those first quiet cracks we sat with only a little while ago. But I do know this much after spending an entire billion years finding it out together. Whatever it is not nothing. It never was. If tonight's story kept you company for a little while, made the room feel a touch warmer, or helped your own thoughts finally slow down enough to drift somewhere quieter, it would mean a great deal to me if you left this video a little kindness on your way out. Like a comment, whatever, feels natural, and if you are new here tonight, consider staying a while longer. I always love hearing where you're watching from, or what part of tonight's story happened to sit with you the longest. So if you have a moment before your eyes finally shut for the night, I would truly love to hear about it. I have another chapter of this exact same story, waiting for you, one considerably colder than anything we covered together tonight. An entire planet freezing over so completely that some researchers believe ice may have reached almost the whole way down to the equator itself. I think you will want to be here under soft lights and quiet background noise, exactly like tonight when we finally step into it. For now, though, let the water settle, let the colours fade quietly back into stone, and let yourself finally drift off into whatever comes next, the same way this entire patient planet always has one quiet, uneventful, absolutely essential moment at a time. Thank you for spending an entire billion years with me tonight and for staying all the way to this last quiet shoreline. Rest well wherever you happen to be listening from. I will be right here waiting with the next chapter whenever you are ready to step back into the cold.